Good morning, Axel. Can you hear us? Axel, can you hear us?
Yes, I can hear you well.
Great. I think we're setting everything up now for Mike.
Yes, I can hear you well.
Are you out of bed?
Yes,
Right.
yes, yes.
I think we're setting everything up now for Mike.
Are you out of bed?
Absolutely.
Yes,
Yes.
Are you out of bed?
We seem to hear some feedback and repetitive things.
We should be good again. I forgot to close the YouTube window.
1, 2, 3, test. 1, 2, 3, test.
We're good.
Richard, what's your email address?
It's fantastic work going on here. It's
Good morning, everybody. Welcome to the third day of the LAMMPS workshop. It's been going great so far. I'm looking forward to lots more good talks today. I have a specific announcement for people who are participating in the poster session. So we are going to have later this morning, we're going to have 1 minute lightning advertisements for each of the posters. And so we're going to have people, all the poster presenters come up on the stage here and one at a time speak at the microphone, explaining in 1 minute what their poster is about and why we should come look at it. If you want, you can send Richard Berger a 1-slide summary of your poster that we can display up here while you are speaking. If you don't want to do that, that's fine. If you've done it already, Richard has it. If you still would like to send it, his email address is rberger@lanl.gov. That's rberger@lanl.gov. Sorry, we can't display that, but ask Richard for the email if you get stuck. With that, I'm going to hand it over to our session chair, Rich Wood.
should be good.
Good morning. So far, great discussions on all of the talks, and I hope to meet and chat with more of you, and hopefully you're finding new collaborators as part of this workshop. We're going to start our session with someone who probably doesn't need an introduction. Mike Klein has a number of contributions to the field that are too numerous to list. Some of those that I was struck by when I was reading his bio was that he's contributed to science in more than just papers. He's put out more than 150 students, postdocs, and others who find themselves in mostly academia, but industry and national labs as well. So the impact on science is beyond the papers for Mike. He's also a member of the National Academy of Sciences. He had a stint as the Dean of Science and Technology at Temple University, taking it to one of the premier research institutions in the world during his stand. With no further ado, Mike.
Thank you. Good morning, everybody. Challenging. The only other place on the planet I've given a talk at 8:30 a.m. is Atomic Energy of Canada. And then you had to drive 120 miles into the bush to get there in time to go through security and then give a talk at 8:30. So welcome. The history of computational science is inextricably linked to computers. And the foundations of the field were laid by mathematicians in the 1930s. Key event, 1931, Alan Turing went to university to read mathematics. Another seminal event, 1932, Claude Shannon went to University of Michigan to read mathematics and electrical engineering. He was 16 years old. Astonishing. He came from rural Michigan. Turing's career, I don't have time in the short window for the talk to go through, but probably most famous for the work he did as part of the team cracking Enigma code. But he wrote a paper soon after he graduated. He was still an undergraduate on the decision problem. And unbeknown to him, he was scooped in this by a mathematician at Princeton. I'll say a tiny bit about. We celebrated 100 years of Turing's birth in 2012. Just briefly, Turing, as you'll see up there, in his paper, said computable number is essentially one that can be expressed as a decimal in a machine. The paper that scooped him was by Alonzo Church at Princeton, founding editor of the Journal of Symbolic Logic, who published in the first issue of that journal his paper on effective calculability. So when Turing wrote up his paper, so after he graduated, he got a research fellowship at Cambridge. They're quite common. You often get 5 to 7 years to do what you want, go where you want. And he took a course on logic from a mathematician at Cambridge, Max Neumann, whose family had been refugees from Nazi Germany. His original name was Neumann, not von Neumann, and he anglicized it to Neumann, a famous character. And Turing gave him a copy of the paper. Unbeknown to him, that Neumann knew Alonzo Church and knew Alonzo Church's papers, and he showed Turing this paper. And then I've highlighted in blue there what Neumann wrote to Church, that Neumann's paper caused a lot of distress for Turing. So at the end of Turing's paper, he acknowledges Church's work. Not only that, he then went and did a PhD with Church at Princeton. And he did a PhD in less than 2 years. Claude Shannon was another genius that got out with his dual degree and then went to do a master's degree at MIT. His master's thesis was doing the mathematics, the logic of essentially printed circuits. This original work was presented at conferences and published in 1938. That thesis at MIT website has been downloaded over 100,000 times. Just to tell you, one could argue that this is the greatest master's thesis ever written. And this set out the whole logical way to do a circuit, and instead of doing it arbitrarily. And as he says in the paper there, he's using the calculus of propositions which come from symbolic logic. Just go back a minute to here. During the Second World War, he worked at Bell Labs on trying to encrypt, and it was the telephone company, and they were charged with trying to get Roosevelt and Churchill to be able to communicate secretly. And because of that work, it turned out that Turing was working on the Enigma code and so on in the UK. He was sent to the US for a couple of months, and he spent a lot of that time at Bell Labs, overlapped with Shannon. It would have been wonderful to be the fly on the wall. What did these guys talk about? I mean, they were both introverted nerds. Apparently they had tea every day. It would who knows what they spoke about, but they did stay connected. About 10 years later, just before Turing committed suicide, Shannon invited Turing to write a paper in an edited book he was doing. At that same time, a couple of engineers at the engineering school at UPenn embarked on building a computer. Actually, I think the title ENIAC was the last C, and it was actually calculator, I think, not computer. And this took 3 years to build. And because it was the wartime, they were kind of forced to hire as technical people, female mathematicians. I actually learned about this when I read the obituary of Kay McNulty, who died in 2006. I was unaware of this until I read that obituary. This was an engineering marvel, weighed 30 tons, 5 million hand-soldered joints, and it worked, and was delivered to the US Army, Aberdeen, Maryland, about halfway between Philadelphia and Washington. The computers were the women, that actually there was no coding. You had to rewire the machine for every task. During the construction of this machine, the inventors, Presper Eckert and John Mauchly, they were already planning the next machine. And von Neumann muscled in on this because he wanted to have such a machine, the next generation, built at Institute of Advanced Studies. And he took it upon himself to write a report on this soon-to-be machine, which he went around publicizing. in my view, looking back at the history, kind of shamefully adopting what these guys have done. But he was a consultant to everybody, including IBM, and that's how IBM was able to keep abreast of what was going on, my interpretation. Anyway, von Neumann publicly said that Turing's machine was simple and neat, but didn't tell him how to build a computer. However, that never stopped von Neumann going around lecturing on Turing's machine. I managed to find copies of his lectures he gave every summer at UPenn in the 1940s about Turing's machine. Did I miss one? Yeah, so then we had the MANIAC computer, which took, again, another 3-year effort, but this was massively lighter. It wasn't 30 tons, it was half a ton, still pretty heavy, and was delivered to ENIAC. And that signifies the beginning of our field, basically. However, in parallel to this, what was going on was the commercial enterprise of trying to build commercial computers. And the first commercial computers were actually built in Philadelphia by Remington Rand Corporation. Interesting factoid, the person in charge of buying up the 2 existing private ventures at that time was the same guy in charge of building the bomb at Los Alamos, General Groves. And he was the one that brought these sort of rogue companies to fruition. Story for another day and another time, particularly with a drink in your hand. Anyway, that brings us to the birth of really what I was talking about. And I was asked to focus on the 80s and 90s, but I can't avoid acknowledging these pioneers. And those of us in the early days of this field wondered who invented the algorithm and the Monte Carlo, because a group of people don't sit around and invent an algorithm. It has to come, the germ has to come from somebody. And it seems clear now that it was Ariana Rosenbluth, although for many years, if I even go back 40 years, Bernie Alder claimed that he invented Monte Carlo. And there was a meeting in Vienna in 1985 where a group of us, including Dan Frenkel, challenged Bernie to explain to us what he actually did. And in fact, it wasn't important sampling. And anyway, he went to his grave believing he invented Monte Carlo, just randomly inserting something. Of course, in a dense system, that's a very improbable event. So anyway, but there's a footnote in the paper, which I think a lot of people ignore. It actually acknowledges talking to Bernie Alder and Stan Ulam. So maybe in his memory, Bernie imagined this talking to them, he was part of the invention. It's quite clear when you look at the literature, there are lesser known papers by Ariana and Marshall Rosenbluth, where they use this machine to do other things than what they're famous for. Bernie's claim to fame is real. I mean, his paper on molecular dynamics for hard sphere systems. I interacted with Bernie quite a lot in the 70s. Bernie wasn't interested in anything that didn't involve hard spheres. So in fact, that's probably why he missed his Nobel Prize, but he just was obsessed with hard spheres. Journal of Chemical Physics has just put out a list of 90 papers over the 90 years of the journal, and this paper of Bernie Alder Wainwright paper. You can find in the CCAM website links to talks and interviews of people involved, and encourage any of you interested in the history to go and check. And also the Frenkel Baron Smith book has a chapter on the prehistory of computing, which is a good read. That brings us to the 60s, which is kind of my decade. I started research in the summer of 1960 for an undergraduate thesis. And the 60s brought us molecular dynamics of solids and liquids and the density functional theory of electronic structure. All things that underpin what we all do today. So as a graduate student, I was sent to a conference on lattice dynamics. And at that meeting, George Vinyard from Brookhaven National Lab showed a movie of radiation damage, channeling of energetic particles coming into a crystal. This paper, if you look it up, has the same algorithm that we often call the Verlet algorithm. And a few years back, Jean-Pierre Hansen and Dominic Levesque wrote a paper showing that the Vallet algorithm is exactly the same algorithm that Newton used to integrate planetary motions. So we should call it the Newton method, because that's what it really is. And way before Vallet, we have this paper from George Vinyard and his group that invented molecular dynamics. At that meeting that I went to as a graduate student, Ewald gave a talk where he said, it shouldn't be called the Ewald method. He said, we were all students of Max Born, and after lunch, the group went for a walk. And that was the only time the group could communicate with each other, because we all worked in one room at our desks. We had to be silent while Max Born had a sleep at his desk. If we talked, we would wake him up. On one of these walks, I was explaining to Peter Debye that I was having trouble getting an asymptotic series of 1 over r to the n to converge. And all Debye said, think reciprocal space. So that was the story Ewald told in 1963. I met other people there. Soon after that, in the Sraman's paper, which in many respects, looking back, was more psychological than a massive achievement. He did have a system of 800 particles in a box, and he ran it on both an IBM 704 and a CDC 3600. 8 years later, I was using a 3600 Atomic Energy of Canada lab, still running, and it was the best machine in the whole country still at that point. Just a word about Seymour Cray and that machine. Cray was one of the group that left Engineering Research Associates in Minneapolis and joined, well, actually made the Control Data Corporation. And he was a designer of the 1604, the CDC 6600, and the other series, and also the 7600, which were big machines that some of us may have known about and even used. I mostly used this 3600 that was at Atomic Energy of Canada in the early days I was in Canada. The next summer I was lucky enough, I just finished my PhD, submitted it. I got an appointment at physics at Rutgers University, and my boss there, George Horton, sent me to a summer school on many-body theory at the Atomic Energy of Canada lab. It was held. They had a thriving theoretical group there. And I heard Walter Kohn lecture on Honeberg-Kohn theory. In the audience sitting beside me was Lou Sham, who just graduated the same year as me. And he was about to go off to be a postdoc with Walter Kohn. And that's history. Kohn-Sham orbitals came out of that with this massively popular paper. A couple of years later, I came back to the US for the summer to work again at Rutgers in the physics department, and I did a mini tour of the US visiting the national labs. And why were people interested for me to come here in 1966 and give a talk? Well, one of the chapters of my thesis was concerned with how you define the thermoelastic properties of materials under stress. Why was I interested in that? Well, my thesis project was about zero-point energy. And intuitively, when you think of an atom not as a point particle, but being puffed up because of zero-point energy or wave function, I thought, well, to understand what happens with the zero-point energy, I should first do the reverse. What happens when we compress something? So we can understand negative stress. It led me to spend several months going through the research literature on elasticity back to the pioneering work of Cauchy in French in the 1800s. And I wrote a chapter in my thesis, which was to summarize all this. My advisor, Hugh Barron, thought this would be of general interest. It got published, and I guess a couple of years later got discovered, and I was invited here to talk about materials under stress. It brings us to the age of the 6600, which was the fastest computer in the world for some period. I was talking to Gary. Did you get to use this? It was the fastest machine in the world in the 60s. Again, Seymour Cray designed machine. I'd already mentioned in the first machines, the 3600, that Seymour Cray believed that if you were going to sell a machine for millions of dollars, it should look special. So the 7600 had these glass panels, which would look like sapphire, and it had walnut trim on it. So you could add another few $1 million to the price tag. Fabulous machine. So end of the 60s, we started to think about molecules instead of atoms. That meant chemists got involved, not just physicists. And I moved to Canada in 1968 to put my first permanent job. And I connected with John Barker, who at the time was in applied math at the University of Waterloo. And John told me about the calculations he was doing on liquid water. This was the first publication of a simulation of a molecular liquid. Sadly ignored. It's totally ignored. It's been overrun by the subsequent work I'm going to talk about. So as we entered the 1970s and we wanted to study molecules, the real issue was, where do you find computers? So here the pioneering work was Frank Stillinger. He was at Bell Labs, and he tried connecting with the academic community to try and persuade people to model water, in particular Bruce Byrne, who all said, no, we don't have the computer time to give you. But Anise picked up the challenge, and then there are a couple of papers in the early 70s on water. And these papers are included in this collection of the significant papers in Journal of Chemical Physics. I don't have time to say very much at all about the move into biology and biophysics, but biochemistry, biophysics, but this was certainly stimulated by the modeling of water. Herman Berenson, behind the scenes, was the guy pushing a lot of this. He also pushed computation. The seminal paper for me was Peter Roski spent a couple of months in the summer of '76 at a CCAM workshop. Herman Berenson and company were there. He was working with Anise Rahman. At the same period, at the same time, I was actually on sabbatical at University of Paris. I was in the theoretical and high energy physics group. They had their own personal UNIVAC 1108. So all of my molecular dynamics calculations done in collaboration with Dominic Levesque and Jean-Pierre Hansen were all done using this UNIVAC 1108. It had a beautiful tape system where we could store our data and then go back and run time correlation functions and so on. Just a word about Peter, because there's a really strange factoid here. So as Peter, in his own words, in 1976, Karplus got in touch with Rahman and sent Andy McCammon and Peter to spend the summer at CCAM in Paris, working with Anise. And what came out of that was the CCAM report, which is published the following year, where there's a chapter in that by Peter Roski and Anise Rahman modeling a dipeptide in water. When the publication appeared in the American Chemical Society, it appears as Roski and Karplus, and Anise Rahman disappeared. I never got an explanation from Karplus as to how that happened, but anyway, he got his Nobel Prize. 70th brings us Cray. Seymour Cray, he got upset with the people at CDC that wouldn't sponsor his thing, so he moved on and created his own company and built the Cray 1. It was the 70s, so if you look at the clothes he's wearing, and that's why I colored it purple. 70s were different. So he managed to sell these machines for $9 million each. It was referred to as the $9 million love seat because of the place around it, which was for the cooling system. He believed to make fast machines, you had to make them smaller and more compact, and the challenge was to cool. And he had liquid freon passing through the system to cool it. A really novel idea. Can't leave the 70s without a shout for Shake, the beautiful paper on how to handle chain molecules instead of using torsional potentials, using holonomic constraints. This is a massively cited paper. And these guys, it was Jean-Paul Ricard's thesis, and Giovanni Ciccotti was around at CCAM at that time. And Herman Berenson was the driving force for getting this done. And Giovanni solved the problem, the mechanics problem of how you let the equations evolve and then you refix all the bonds. So that shake. If you go on the web, you can find a lecture by Jean-Paul and Giovanni. But I caution you, you have to learn Italian Sign Language if you're going to get anything out of this video, as you can imagine. Let's skip the 70s, the rest, because, you know, the 70s was special. So that brings us to the 80s, nostalgia. Do you remember, any of you remember these things? They lived a long time after the 80s, but it was different, right? I know that I wired my house with Apple Network, and I had 2 Apple computers in my house in the 80s. Actually, they were expensive compared to salary. That's one thing that's happened, right? We might think this phone is expensive, but compared to your salary, it's not. So just another couple of factoids. The first laser printer came out, it was $100,000. So that's gone down a factor of 1,000. And the gigabit hard drive, first of all, it weighed 3 times me, and it cost $40,000. So this has got 1,000 times cheaper for 1,000 times more memory. So we've gained a factor of 1 million just there. 1980, Michele Paranello decided to go and spend some time working with at Argonne National Lab with Anisur Rahman, and that changed the field, I would say. So that's the Reagan years. So finally, I'm into the 1980s, and lots of things happened. I can talk just about a few of them. Hans Andersen's paper was really important. He brought us the extended Lagrangian, how you could add extra variables into the dynamics. This was profound. In fact, when Hans retired from Stanford, I was asked to give the after-dinner speech. And I wrote to Michele Paranello, I said, Michele, can you give me a sentence or two about what I can say about that? And he said, this paper created my life in science, the extended Lagrangian. So, I mean, Michele is not famous for writing long things. That's what he said. So profound. He had profound influence. So the Gordon Conference that year on liquids, I was a speaker there, so was Anis. And you gather outside on the grass, and Anis came running across the grass, waving the Mike, look. This is what I've just done with Michele. You've got to do this for molecules. He'd done it for ionic solids and then other solids. If it had been easy, he would have already done it. So it took us 1.5 years. I had to learn about quaternions. Even focusing on rigid molecules was not so trivial. In the meantime, this seminal paper came out, the pair of them, and what they'd done. And then our papers came out on materials under pressure, watching it crystal. But we were focused there on small molecules. Shuichi Noze joined my group. He with Roger Impey, wrote the codes that did that. It was beautiful to be able to set up a system and let it find its own equilibrium. Shuichi spent 2 years with me. He published 12 papers. Incredibly brilliant, probably the most brilliant postdoc I ever had. It enabled me to do a collaboration with Bill Jorgensen. Roger Impey wrote a general code that had long-range forces and other things in it, and it enabled us to connect with Bill Jorgensen, who was doing constant pressure work. And of course, we could run diffusion constants and other things. Really, this was the culmination 50 years later of the seminal paper, one of the 90 special chosen by JCP of Bernal and Fowler, pioneering paper. Shuichi came to my office one day with a couple of articles written on how he wanted to do canonical molecular dynamics. And I told him to take my name off the papers. I could never have dreamed of doing this. Okay. And these were incredible papers. And again, Shuichi Noze's paper was one of the ones selected for this special issue. A shout out to work done by Don Frenkel, constant pressure Monte Carlo, phase diagram of, he had in mind liquid crystals. And then in '84, we celebrated Anis because he was terminally ill with cancer. And we had a conference where we invited people. I was one of the organizers. And at this meeting, anybody who was anybody was there. Gary Gress was there. There's the proof. Martin Karplus was there. Michele Parinello was there. Charles Bennett was there. There's Gary again. There's me with Don Frankel. And Michele Parinello was hiding in the back in this picture. There are lots of other luminaries there. 2 Nobel laureates in this picture. They were not Nobel laureates at the time, John Popel and John Polanyi. But there was another Nobel laureate that I showed you earlier, Martin Karplus. So 3 of the people at this meeting got Nobel Prizes. And I don't think we've seen the last. So those days were special. Internet wasn't really that powerful in the early 80s. Anise and I communicated on punch cards. Here's a picture of a punch card in my pocket. We would scribble notes, either put a postage stamp on the card and send it, or put it in an envelope and send it. And here's the proof. I work for the government, so my mail was opened. And you'll see here the timestamp received at the National Research Council. And when he wrote me a card, he just used to address it, Mike Klein, Sussex Drive. Didn't he say the building? Didn't say the number? Obviously, the Secret Service knew who I was. I had many visitors from the Soviet Union during this time. So the Canadians knew who I was. The next year was Carl Parinello, changed the field. Can't resist showing another Cray. Remember I said Cray thought his machines should be arrestingly beautiful. This is the CERN Computer Center in the 80s. Shout out for this incredible decades of work by Gary and Kurt Kremer on polymer systems. Again, Gary's paper with Kurt chosen for the special issue. Important things happened in the 90s. My group contributed something in the field of algorithms. Both these papers are part of this special issue. We again came to graphics in the 90s, silicon graphics. Silicon graphics enabled us to render beautiful images. And the guy in my group that did that, the work was the last student of Anisur Rahman, who after this work became a successful commercial artist. He paints wildlife. So it happened to me one day, I got a phone call saying, I won't be coming to work today. This was Joe. I'm going to meet the president. I got to go buy a suit. The president of what? The president. He just won a competition for the federal duck stamp. And he was the guy that made all these images in my lab. So he was good. But the guy who wrote the software was graduate student John Shelley that enabled us to render surfactant systems. We could also render electronic charge distributions. Here's a picture of a bipolaron in a polar solvent. We could watch the metal insulator transition by adding more electrolyte and see the electronic bands go all the way through the liquid. Beautiful things happened here. People were worried about getting great software. Shout out to Steve for this monumental work. Also in the 90s, we had John Padu's PBE paper, 220,000 citations. Probably when I get back to my lab, you're going to find this number's gone up as you look at it. Got a shout out for Seymour Cray. This year marks the 100th anniversary of his birth. I don't know that anybody's celebrating that. This guy changed the field completely. His name is synonymous with supercomputer. I'm going to skip through just quickly. We've got some great memories. I can't stop without saying I want to highlight this paper of Michele, which was stealth. Nobody paid any attention to it for at least 5 years, at least 5 years. It was just sitting there, unnoticed. Fabulous contribution. Now it has 5,000 citations. You guys have contributed phenomenally here. I'm thrilled to see you work with Gabor Chanyi, who is one of my heroes for what he's done in UK. I regard myself as a silent partner in LAMMPS. I have not contributed anything other than emotional, maybe. I'm thrilled by the success. Here's a paper with 9,000 citations in just 2-3 years. This is amazing. Say hi to Axel. Hello, Axel. And last slide, if you go to the list of top 500. 4 of the top 5 have the name Cray associated with them. So when I gave a talk about Cray at Princeton recently, a couple of people came up to me and said, I didn't know that Cray was a person. I thought Cray was a computer. And there you go. Okay, I'm done. Well,
I'm more than happy to ruin the schedule after just one talk, because that was quite delightful to get a recap like that. If there's questions in the room, I can come give you a mic. If there's questions online, if someone could flag me, and we can repeat the question for Mike.
I'm sorry I went over. I just had a lot of ground to cover.
No trouble. 80 years is a summary of our field is a lot to cover.
Is this in a book anywhere? Like a history of this written down would be fantastic to work through.
So I have, if you go to Mike Klein YouTube, if you Google that, especially when I go to Asia, they seem to tape my talks and put them on YouTube. You'll find several. One is called The First 30 Years. And just Michael L. Klein YouTube, and you'll get more than you need. Instagram, TikTok. I don't do it. I mean, other people do. I lived it, so it isn't so difficult. You know, I knew Walter Cohn, and I was perhaps an unusual student. I was a chemist, but when I entered chemistry, was only doing the gas phase. But I knew chemistry of mixing liquids or putting solids in liquids. But everybody in the lab was worried about diatomic molecules in the gas phase, because that's the only place quantum mechanics work. So I became a groupie in physics. Physicists weren't interested in liquids back then. They were interested in solids. So I thought, well, I can go from solids to liquids. And so I was blessed with the people who taught me at in Bristol. Incredible characters, people that had overlapped with Leonard Jones, who's a person, not just the potential.
Mike, I have a technical but very broad question for you. Why do you think that when you look at these many decades of molecular simulation, at the start it was split 50-50 between molecular dynamics and Monte Carlo, and now it's dominated by molecular dynamics? Do you have an opinion about that?
Yeah, so Monte Carlo, looking back for us, was easiest to enter. In fact, after my contact with John Barker, he encouraged me to do I was interested in molecular crystals. So I did work on nitrogen and carbon dioxide. In fact, that paper of mine on carbon dioxide from way, way, way back has been rediscovered. Everybody's worried about carbon dioxide, but we got an intermolecular potential for carbon dioxide, not particularly good, but so it was easy to program. The only thing that some of us were obsessed with, how random should be the random number. So I spent a lot of time talking to it. And as they say, random numbers mainly fall in the plane, in the famous song. Okay, the rain. Anyway, in the end, it doesn't matter because it's statistical anyway. So that took us months, if not more than a year, to get over that. Should they really be random, or does it matter that they're correlated? So we use random numbers to pull random numbers, and I mean, it didn't matter. So that was the easiest to get into. The other issue was storage. Where are you going to put the data from your molecular dynamics? Because you want to do time correlation. Otherwise, what's the point? So as I showed that picture of the 1108 that had tapes. So it wasn't uncommon to do a trajectory that ran the whole weekend, right? We weren't allowed the time during the week, but had the whole weekend. You come in the morning and one of the tape drives failed. So you've got to wait another week. So that was why early we did quantum Monte Carlo, we did quantum, it just was easier. If you kept the configuration, it was a box of cards.
Now we don't need easy anymore.
Right. It doesn't matter, right?
Yeah.
Yeah.
Okay, let's thank Mike one more time.
You rescue that.
Yes.
Okay. Thank you. Well, 15 minutes, right? Yep.
Our next speaker is Tommy Sewell from the University of Missouri. Take it away, Tommy.
All right. Hi, all. As Mitch said, I'm Tommy. Boy, I feel unworthy following Professor Klein. But there you go. So what I'm going to try to do today in 15 minutes is tell you a story of how we've developed some atomistics, molecular dynamics, mostly determined material models for use in continuum simulations to predict and hopefully understand the shock response primarily of energetic materials for use in continua. And you know what I want to try to do, I'm going to be moving at warp speed, I'm afraid. And I apologize for the people online because you won't see my laser pointer, I assume. But I want to get at some questions here. You know, how are we doing? How do we know how well we're doing? And ultimately, how good is good enough? And I'll answer the last question now. I'm a physical chemist. It's never good enough until you've done everything with quantum dynamics, right? I'll also mention I've never met Professor Kohlmeier, but it seems that he and I are kindred spirits in a few ways. All right. So a long time ago, on Tommy's time scale, not Professor Klein's, I was at a workshop, and Dana DeLotte, a experimental physical chemist at Illinois that many of you would know, I had given my talk. I was very proud of my elastic tensor. It is a function of temperature and pressure and so forth, a few other things. And if you'll excuse me for attempting to channel Dana, gee, Tommy, you theory and simulator types always seem to characterize your results as being in reasonable, good, or excellent agreement with experiments. What does that mean? How do you know? And how good is good enough? And I probably stammered out some sort of lame response at the time, but Dana's question remained with me, right? I mean, you know, we're always in the pursuit of, I don't care much about knowledge. What I really seek is understanding. And so I owe Dana a certain debt of gratitude for that, actually. So we're going to talk about high explosives. My talk today will focus on one particular energetic material called HMX. I'll just call it HMX for now. I'm a physical chemist, not an organic chemist. But what a real explosive is typically plastic or polymer bonded explosives are very highly filled polymer composites in which the energetic constituents are small crystallites that are suspended in a typically polymeric binder. The spatial, too many buttons. You know, the spatial scale of these, that's a 200 micron space bar. And you can see that this is a complicated material. I think it's actually complex in the correct sense of the term. You have lots of crystallites with a wide variety of particle sizes. And you know, question is, how big of a piece do you need? So, you know, let's kind of break it down a bit. So there's a starting piece of PBX. If you zoom in on a piece of crystal down to the order of 100 microns or so, you're getting into the realm where crystal defects and dislocations and things enter the picture, going down a fair bit more. And you know, now what can this be? On the order of a micron or so nowadays. We can do all atom molecular dynamics. This is a lot less than a micron, obviously. And ultimately, the properties of the material are born at the level of the molecule and the crystallographic unit cell. So it's very much a multi-scale problem. And you know, the question is, how do you take information that we can obtain from this scale and ultimately get it up through this scale? And of course, you know, a really hard challenge is this intermediate scale. Tell me that you're simulating plasticity, and I'll go somewhere else probably. I've said most of these things, but you know, predicting the shock initiation, it's an emergent phenomenon, is truly challenging. And another problem for the people who are developing models is that even, you know, the fundamental data for these materials are sparse. You don't have that much information that you can validate your predictions against. And even if you do have data, more often about fundamental data, those data are generally limited to the you know, room temperature or maybe a few different isotherms. There's, you know, you have to work hard to convince yourself that your models are reasonably predictive for the molecular dynamicist, because a lot is going to hinge on that accuracy. And also, in instances where you have multiple experiments on the same property, the data are often quite inconsistent. And I would argue that with a good molecular dynamics force field, as long as you're not looking at properties that are strongly affected by quantum effects like the heat capacity, these are molecular materials, or the Gruneisen coefficient, we can often tell people which experiment is correct, right? And I think that's not a huge assertion to make. So we had a Muri a couple of years ago. It ended about, formerly the no-cost extension, ended a few months ago, where we, a team of physical chemists and engineers and computer and materials type people wanted to tackle this multi-scale problem in a deliberate way, right? Focusing on fundamentals and taking that information up. And so this is the cast of characters. And what we sought to do here was based on atomistic methods. We want to develop a model that properly captures mesoscale phenomena, and on the larger scales is microstructurally aware. You saw the composites. They're not ordered regular materials. What I mean by meso-informed is understanding the fundamental properties and behaviors of small crystals, including the effects of defects, small aggregates of crystals, and then microstructurally aware. You know, we can handle different microstructures on roughly the millimeter spatial scale, which would be the homogenization scale for these types of materials. This was an extremely challenging but very fun project, largely because of these folks. What I want to talk about today focuses on things that my co-PI, Uday Kumar, and Catalin Piku at RPI have done. So what we want to do, as I said, go from the molecular scale through the meso scale, touching up to the RVE, and then eventually with homogenization and closure, predict things when they go boom. So the main role of the atomistics people was to provide fundamental material properties, detailed microscopic simulations of dynamic phenomena, and so forth. Dana and Vikas Tomar were, let me get that up, focusing their attention on the crystal scale up to the, again, sort of RVE scale. Dana has some beautiful techniques that let you look inside of an explosive as it's being shocked and beginning to undergo initiation. So what I want to do first is talk about what I'm calling phase one. You know, what are the properties that are really critical to include in your continuum model if you're to reproduce the ground truth as determined by classical molecular dynamics, okay? Non-reactive classical molecular dynamics. How well are we doing? That's an interesting question now. So we are focusing on a problem of shock-induced pore collapse. We basically did a reverse ballistic scenario where for a few standard problems where a sample containing a pore impacts a reflecting wall. It's actually a piece of crystal that's unable, that we've restrained to be fixed. And then the shock wave propagates through. Everything that I'm going to talk about today as regards MD was based on the same non-reactive so-called Smith-Barrett-Waj, it's sort of an OPLS type force field that was developed by Grant Smith and his group for HMX. And all of the simulations were performed using LAMMPS and the large majority of the analysis using Oviedo as it happens. This was the first stab, and some things got cut off. The continuum models were not completely consistent with the MD, and we know that. But thinking now about how this stuff evolved over time, so we're going to treat MD as ground truth. I'd love to argue with you about that, but our purpose is to develop an internally consistent, complete ecosystem for understanding what are the pieces of information that we have to include for a continuum description to replicate the results of an MD simulation, okay? And so if we look back 25 years ago, people were using a very simple model. You had a very small yield stress for the material. It was a constant. And so we have MD prior to complete collapse of the pore, and then at the instant of complete pore closure on the top. For the Minikoff-Sewell model, because the yield strength was so small, pressure and inertia dominate the phenomenon, and the response is essentially hydrodynamic under all conditions. In this paper, what we did was we constructed a systematic hierarchy of improvements, increases in fidelity in the continuum description. And the first thing, and what do you see here, by the way? You don't see any real signs of localization, right? You know, again, it's hydrodynamic. The next thing we did was we replaced the constant yield surface with a Johnson-Cook description for the strength, where the yield stress depends on the local strain rate, and the temperature relative to the melting point for the material at a given pressure. At this point, because you have now a non-trivial strength, you get localization, but it's very, very diffuse, okay, in comparison to what the MD does. All right. Now, the melting curve, the temperate pressure-dependent melting point that was used in this model harkens back to this earlier description, and the dependence of the melting point on pressure was very small. If we substitute a melting curve that was generated by Matt Kroonblad at Livermore, well, the melting points predicted by MD for the same uniform force field everywhere are a lot higher. And so lo and behold, we now get much stronger energy localization. This is starting to look pretty good in comparison to this. So we're learning a lot, okay? And if we add a pressure-dependent shear modulus, it makes some difference, but not a lot. I'll just mention this. So this is the original melt curve that Ralph and I deduced. Here is Kroonblad's melt curve. And you know, what's 1,000 degrees among friends at 10 GPa? Okay. Another thing, and this is critically important, is that we're doing classical mechanics. This is a specific heat, so it's constant, and it really is. Whereas quantum mechanically, the more accurate representation will look something like this. So what's this going to do? It's going to affect the temperature you achieve under a given energy deposition and so forth. I think, because I don't want to be shepherd hooked, by our chair is I'm going to skip through fairly quickly. Using our model, we did a lot of interesting things, but things weren't completely right. And if you want to go back and look at some of the slides, I sort of walk us through it, bringing CADL and PICU into the picture. And I'll take us to the final slide. There's a lot going on under the hood here, but these are now simulations for the using a much improved material description, all completely determined. Everything in here now is determined by molecular dynamics. No made up parameters, okay? And we look at the problem of shock-induced pore collapse now in elongated pores, where the orientation of the pore relative to the shock vector is 4 different values. And here, so here are the 4 different pore orientations. In the top, I'm showing temperature, in the bottom, pressure at the instance of collapse. This on the left in each figure block is MD, and on the right is continuum. Head-to-head, identical system sizes, sample domains, and boundary conditions. I think that we've made fairly good headway, right? If you were to spend a minute and linger, these fields are in really, really good agreement, I would argue. But we're not there yet, right? This is purely classical, okay? And there's no chemistry, but we have ideas for how to get those things. And the chemistry problem is really hard, right? And you can't just plug in, say, a React model on top of this. It will no longer be internally consistent. You can use it as a kind of a guidepost, but ultimately all of this would need to be done using the same reactive potential, whatever that might be. And really, it should all be done using something like path integrals so that you properly account for the quantum effects. The effects of treating the specific heat and the Gruneisen coefficient classically are pretty significant on the temperature. And if we're interested in chemistry and chemical reaction rates go exponentially with temperature, blah, blah, blah. I'll stop with this, only 2 minutes late. And
Thank you, Tommy. Questions in the room or online for Tommy? While we also have our next speaker, Matt, get set up. So MD has gone a long way to be able to compare directly to a continuum simulation. Is there still room where MD has to improve to be in better agreement with a continuum or experimental study?
So it depends on how good the data are, how consistent the data are. Again, does the MD have to improve? Yeah. For organic substances, you've really got to do this with a quantum approach, and I'm calling path integrals that. You're not going to do TDSE directly anytime soon, right? But certainly path integrals are readily accessible for this sort of thing, especially for you guys at national labs. But what we really want to do in the end of the day is we want to get right answers for correct reasons. We don't want to do calibrations. We want to get things right for the right physical reasons, including the correct physics in our continuum models. We don't want to make stuff up.
Thanks for that answer.
And your mic.
What?
Oh, I see. Okay. Just to the desktop.
Mhm. Or you're an SMD assistant.
Oh boy.
So you have to allow that. And then you have to reconnect.
Sharing permissions.
Still. First. Yep. Oh, arrow.
Okay.
Still allow thing.
Oh,
Share.
great.
Okay, our next speaker will be Matt Lane from Sandia National Labs, talking more on shock physics and what we can learn from MD for that problem.
Okay. Sorry about that. I thought I had this all set up. I'm from Sandia National Labs, and obviously laptop security is a priority at Sandia. My name's Matt Lane. I'm going to talk today about using molecular dynamics. I'm going to investigate some apparent violations in the Rankine-Hugoniot equation in highly porous materials, kind of expanding on what Tommy was talking about with extreme materials. And I'm talking about this at the workshop today because I think it's a really nice example as molecular dynamics in recent years has moved increasingly to quantitative solutions and really high accuracy quantum mechanics. This is still an example where fundamental qualitative demonstrations with MD can still be really impactful. So I think this is a nice compact example. So this is, this is cut off a little bit, but so this is a summary of shock physics in one slide. Over here, we see a finite amplitude wave. So any finite amplitude wave in a material, because at higher pressures and densities, the wave speed is higher, you tend to get a steepening of any wave to eventually form a discontinuity. So this is a shock wave, and if you have a shock wave propagating into a pristine material, you can analyze the conservation of mass and momentum and energy moving into this discontinuity and write down some jump conditions here, which when you combine produces the Rankine-Hugoniot equation. And this is basically the definition of a shock wave. So this is written in terms of the internal energy, the pressure, and the density. And if you know the internal energy as a function of pressure and density, in other words, the equation of state of the material, then this reduces to a single curve through all of pressure and density space. And so what this means is that if a shock forms, and eventually it always does, then you can't get to states up here at low density and high pressure and over here. You are mandated to stay along this curve, which is known as the Hugoniot. And this is an incredibly robust theory that's been used extensively at Sandia and elsewhere to study high pressure material response. So it turns out that while this is derived here for a discontinuity, it generalizes to any case where you have a steady state. And in fact, it's so general and so robust that even when you have a steady state on average, it holds on average. And the take-home message is that the Rankine-Hugoniot equation, or the behavior of shock physics, is incredibly robust. And what I'll show today is that in highly porous materials, this actually breaks down. And I'll argue that in these highly porous materials, shock waves don't satisfy this Rankine-Hugoniot and are not rigorously shock waves. All right, so what do I mean by highly porous material? Here's an example. This is silica, model silica at 90% porosity. This is an experimental micrograph of a polymer sample of polymer foam. And then we've also done metallic foams. So highly porous means on the order of 10 to 20% of full density. And the Hugonio response for porous materials is predictable. So if the principal Hugonio is down here, basically as you go to 3/4 of full density and 50% of full density, as you increase the number of pores and they, under compression, collapse, they create hot spots and heat. That heat leads to thermal expansion. And so for any given pressure, the more porous you have, the more to the left you're shifted to lower density. And this process continues, but at extremely low densities, the Hugonio actually turns back. And so if you imagine being on this point right here at the cusp, you're driving a piston into the material at some velocity, and you increase the velocity, the final compression basically decreases. So the material doesn't compress as much as you continue to press harder and harder. And that's kind of, if you're familiar with Hugonio response, generally, as you press harder, the densities get higher and higher. And so this turnback is kind of paradoxical. And molecular dynamics lets us explore what's really going on here. So I'm going to look at two states, one just below that turnback and one just above that turnback, and drive two shock waves at different pressures into the material. In the lower case, below that turnback, you see what's often termed a snowplow, or a more traditional shock propagation. And here the pores are basically crushed out. And so the material compresses, the pores collapse, and you get a final density behind this shock front. But in this upper example, the material vaporizes and it expands into the voids. And so even though the process here of this vaporization and throwing out ejecta ahead of the shock front, even though the process is very different, the final density is exactly the same in this case. And as you increase the pressure, it actually goes to lower and lower density. So this is a nice visual representation of what's going on in this anomalous case. So the experiments, unfortunately, in these materials and in these regimes are really quite difficult for a number of reasons. One of which is sample variability. So because these samples are created stochastically, the sample to sample, you can get variations in the total density. And even within a sample, you can get variation in the pore size and the pore size and shape distributions. And because of that, it's also very difficult to know what the initial internal energy of these experimental foams are, because you don't really have a good characterization of what the foams look like and how much surface is embedded within these materials. So furthermore, if you treat this internal energy as kind of a free parameter and just say, well, we don't know it, we're going to guess it, and then do a number of Hugonios, you can kind of sample the data space of the experiments, which are the triangles. But there's a ton of data out here that you just can't capture without assuming internal energies that are just clearly wrong. And so the Hugonio has struggled to explain the experimental results. And there's been kind of a question as to whether these are really shock waves and whether the Rankine-Hugonio equation is satisfied. So with molecular dynamics, we solve some of these problems because we can get exactly the same initial conditions and drive different shock waves in them. We also know all of the internal energies before and after and in between. And so we can eliminate many of the problems with the experiments and really narrow down to the core question of whether the Hugonio is satisfied. So here's what we're doing. We're driving a shock wave into a porous material. Oh, come on. We're driving a shock wave into a porous material. We've done this for silica. We've done this for polymers. We've done this for copper. And in each case, the chemistry gets very complex because the temperatures get really high. And so what we're actually doing is trying to get at the underlying physics. So we've gone to a very simple model, which is the Leonard-Jones cubic spline. This is a well-known potential. It was first used by, or maybe not first used, but widely used by Brad Holian in his groundbreaking work in the early 1980s. So it's got a really nice pedigree as kind of a nice empirical generalizable material. So we're going to drive dynamic loading in 3 different ways. The first one is called non-equilibrium molecular dynamics, where we're just simply going to drive a piston into the material, and whatever happens, happens. If the material wants to shock up, it'll shock up. If it wants to do something else, it'll do something else, right? It's going to respond however it wants to as an emergent phenomena. We're also going to do a Hugoniostat, which is also a dynamic simulation, but in this case, the equations of motion are modified to always satisfy the Rankine-Hugonio equation, basically to assure that you are on a Hugonio. And then we're also going to just direct solve. So if we know the equation of state, we can calculate the equation of state for our material. We can just plug it into that Rankine-Hugonio equation and direct solve it. So these are the results. This is the Hugonio plotted. This is the same data with kind of at high pressure and at low pressure so that I can illustrate kind of the features in both cases. And so what we see, first of all, is the pink is the Hugonio direct solve. So that's what the Hugonio for this material should look like. The pink dots that fall exactly along that line are the Hugoniostat. So there's good agreement there. And then the black points are the non-equilibrium points. There's 3 behaviors. Down here below the turnback of vaporization onset, you get good agreement with, so this is Hugonio, this is a shock. Here we get relatively poor agreement outside the error bars, and I'll qualify that in a moment. It's shifted up and to the right. And up here at high pressures, it's shifted actually the opposite direction to the left. And just to give you kind of an idea here, if we wanted to shift this Hugonio to agree with this data, we would have to reduce, so the dashed lines are removing energy in blue and adding energy in orange. And we would have to remove a characteristic amount of energy, which is the total porous surface energy in the material. So it's as though the material were crushed out without any heating happening. And so this is a significant amount of energy that has to be removed to account for this shift. And up here, 5 times that amount of energy has to be added to account for this behavior. And so the core take home is that a single Hugonio can't fit all of this data across all of these pressure ranges. And just briefly, so this is attributed to vaporization. I don't know if you can see these red points, but basically beyond this vaporization point, the material vaporizes. And then from that point on, you no longer are bound by propagation by the wave speed, because now you have ballistic ejecta that can travel faster than the wave speed, and it can actually get out ahead of the shock wave. So the shock wave is here. Normally, you can't have any disturbance pass ahead of it, but because this material is moving ballistically, it can carry momentum and energy ahead. And so the kind of the premise of the shock wave is destroyed. So not only are we showing disagreement with the Hugonio, we're showing why, which is that this vaporization and this momentum and energy transfer is non-wave in nature. So I'll just briefly say at low pressures where we see good agreement, it looks like a shock wave, and the material just ahead of the shock the black dotted line is ambient material. Sorry, this is a velocity distribution, probability versus velocity. As we go to higher pressures, basically this ejecta throws energy out, raises the temperature before the compression wave gets there. And if we look at this material now, the velocity distribution shows fast-moving ejecta and the matrix of the porous material, but they are not mixing, right? These are just moving through each other. So effectively, you're losing energy from the shock wave through an evaporative cooling process where energy is just propagating out ahead of the shock wave. But at higher pressures now, that material begins to mix with the matrix, and now this compression wave, it trails the temperature and velocity waves, and so the shock wave is moving into basically a hot vaporized melt rather than pristine material. And we know that it's mixing because this is a Gaussian with a wider distribution. So you're basically preheating the material out ahead of the shock wave. So here's our hypothesis. In a highly porous open pore material, ejected atoms escape the quote unquote shock front and modify the dynamic response in different ways at different pressures. My colleagues, John Carpenter and Svetoslav Nikolov, have put together a very nice continuum scale model to account for this preheating process, which based on time, I'm gonna skip. But the take-home message is if these are the predictions from an equation of state, and these are recent experimental data, there's a significant disagreement if you don't account for this process. In other words, shock analysis does a very poor job of explaining the experiments. But if you account for this preheating process, then the majority of the discrepancy is resolved. And you can do this over a series of porosities and pressures. So the take home is that for very porous materials, shocks are not a good analysis approach. We've been able to show that using molecular dynamics. And specifically, we've been able to show not only that the Hugonio doesn't hold, but why it doesn't hold. So I think this is a nice little microcosm of what MD can do in terms of qualitative understanding. So thanks.
Thanks, Matt. Questions for Matt? Right here.
Hey, Matt, thanks. That's a really interesting study. To what extent do these results depend not on the porosity, but on the pore size distribution and other things related to the way that void? Yeah, I mean, you can create 90% porosity in many different ways. So how does that shift your results?
Yeah. So I'm not making the argument that the preheating is one way that you can kind of account for this and kind of jerry-rig a Hugonio to fit the data. But in addition to preheating, there's also momentum loss and other things going on. So this is kind of a first order correction. But the core take home is that because you're not bound by that shock front, you're not in a Hugonio state. In terms of the variation, because we are in the molecular dynamics simulations, you can have exactly the initial materials. In the experiments, you couldn't resolve this because the variation of the material would overwhelm it. And so in this case, you can account for not only the spread, but those outliers at very low densities.
For time, I'm going to move to the next speaker, but Tommy has a question for you offline.
Yeah, well, let's talk after.
Our next speaker will be Anuja Kim from University of Texas, El Paso, telling us about their MD simulations of ceramic materials.
So, good morning. I'm going to talk about molecular dynamic simulations on aluminum borate. First of all, I'd like to thank the organizer hosting this, wonderful workshop, and Dr. Klein for the beautiful overview of the computational science. Surprising that there was a time that we didn't have a computer, right? So anyway, what we try to do is to design new lubricant materials that can be used for NASA mission. This is Mars rover. As you can see here, there are so many joints and bearing and gears. They are all subject to friction. So at some point, lubricant can be very important, right? And traditional lubricants are liquid like oil, and that can evaporate when it's at high temperature like this, or freeze at low temperature like that. So NASA wants, solid lubricant. So we propose ceramic lubricant based on alumina and boron oxide. Alumina can be a durable foundation because it's naturally occurring with very stable, right? And also it can incorporate impurities like, chromium that makes beautiful ruby and so on. So we decided to incorporate boron into the system. This is a crystal structure of alumina, and see what happened. And this project has 3 components, experimental component led by UNI, and I'm in charge of computational component. And also DRI is leading the education, basically offering student internships. Originally, computational modeling and simulation component had only DFT. We're gonna do DFT calculation to guide and validate experiment. And my student was working on that. And when it funded, of course, I became a little bit more ambitious. So I wanted to add friction simulations that need large scale MD beyond DFT. But that turned out to be very interesting, but also very challenging because of force field. The starting system is aluminum boron oxide, relatively simple. So we thought that there will be plenty of force field, we can use. Turned out that there was none. So we tried to develop force field using swarm optimization, my first postdoc. Then he got job offer from China Lab. And then my second postdoc, he tested all the existing force field. Then he also got offer from OSU. And my third postdoc actually is from Adri Bandrin. He told us that, we have force field for you. It's not published yet, but you are welcome to use. So that's what we decide to use in this case. When experimentalists mix alumina with boron oxide, they synthesize 5 samples. Without boron, 5% boron, 10%, 50%, and 20%. And this is the phase diagram of aluminum borate. And as you can see here, it's quite complex. And they want to make sure that they got what they wanted. And DFT calculation shows that actually we have aluminum borate with stoichiometry like this. Also, we have Raman and IR data from DFT that also confirm that we have this sample synthesized. Using this structure, we started building our model system for friction. But friction is actually very interesting because you can observe it. So you're going to see that, you're going to think that it's going to be macroscopic phenomena, right? You see means that macroscopic. But actually the cause of friction is microscopic. So when object is moving, what happens? There is macroscopic kinetic energy that transfer to microscopic potential energy, transform into microscopic kinetic energy. So there is energy transfer to transform, very interesting, bring you back to freshman year, right? Actually, I got this one from my textbook that I'm teaching. And that's how you see this meteor light, or even earthquake as a stick slip motion, just like a toy choo-choo train. And thanks to Jacob, who gave a really good overview about bonding, potential, right, all that. This interaction between atoms as kind of treated like a spring like this. Anyway, so that is very interesting. So we want to do that computationally. And this is the model system we built. It's something like this. So we're gonna fix this one. And this is our lubricant. And this one, the top layer is gonna move. We added a little bit of extra boron oxide to give more smooth and nice, but because experimentally, apparently, even though the lubricant performance is better for this aluminum borate, but at the end, there is a little brittle things going on, so we added a little bit of boron oxide here. And then we carry out molecular dynamic simulations using MBT ensembles. And we have 5 different moving velocity, and then also 5 different operating temperatures. So this is a simplified illustration of what we did. Of course, in reality, we have periodic boundary conditions, so it's not gonna going like this, but just to show how what we did. And also atoms are all moving, so this is just simplified description of what we did. And we also calculate the coefficient of friction here. This is the color map of the COF. And then as you can see here, it was a little bit difficult to know what to say. So at the beginning, we thought that there will be some correlation between temperature and velocity and friction. But as you can see here, it looks more random than some correlation. So we were wondering about what is going on. And so we actually did elemental analysis. So the size of the supercell that we are using for the modeling is y-axis is like 68 angstrom, and there are 6,000 atoms. So we are really proud of like 6,000 versus, but anyway, compared to 1 million is nothing. But I was very proud. But anyway, so from this is the bottom to that's the top. So the interface between the lubricant and the top layer is somewhere here, right? And when you do the elemental analysis for few different systems, like a 0.1, for example, looks like high in like a friction is high over here. And that elemental analysis says that at that interface here, everything is gonna be, this is the boron, green is boron, blue is aluminum, red is oxygen. They are all in one plane at that interface here. But in case of the 0.2, friction is low here. When you check it, there are, look at that, there is oxygen, red, so oxygen here, and then also aluminum, blue is aluminum. So at that interface, there is aluminum and oxygen, and boron is a little bit below the subsurface. So there are 2 layers. And also same is true for 0.3, which is also high in friction. Everything is in 1 layer. And then 4 and 5, they are low in friction, and they turn out to be all in 2 layers. So atomic arrangement is the reason why friction is high or low. In this case, we checked a little bit more points. 6, 7, 6 is here. It's a very low in friction. 7, low in friction. When we did the elemental analysis, red, just oxygen on top. The next layer is the green, which is boron. Below that is aluminum. So it turned out to be 3 layers instead of 1 layer. Same is true for the 0.3 here, also low in friction, even 3 layers. And then 0.8 here, elemental analysis says that they are actually in 2 layers. So as far as they're not in one layer, this is the original geometry, and after the friction, the final structure for high in friction has one layer. Everything is in one layer. But when final structure is same as the initial or in 3 layers, friction happened to be low. So that was what we found. We also introduced water molecules on the system. As you can see here, frictions are very low, means that water molecule reduce the friction. And also when you check the elemental analysis, at the interface, they are in 2 layers. They are all in 2 layers. There is some mechanism that we published. And we also did nano indentation modeling, imitating the experiment, but I'm not going to go into that due to the time limit. Using this nano indentation, we are able to estimate the viscous hardness. For the lubricant materials, what we are looking for is not only good to slide, but also wear rate should be low. Means that should be good enough to be like hard enough, so you don't lose materials all the time. So hardness and the sliding motion, we try to find the sweet spot for the best lubricant material. Anyway, this is the summary of the aluminum borate. We synthesized a sample, DFT, was able to validate experimental structure and properties. And we also use LAMMPS to simulate the friction. And the results is published in this paper. And then if you need more information, go check this paper or send me an email. Currently, we just got the, what's next of this project is that this is just beginning, the base material for lubricant. There is eventually what we want is like a smart lubricant, means that the lubricant should adapt the temperature and switch the mechanisms. But to do that, we need a little transition metal. We know what metals are supposed to be, but to model these systems, we need force field. So we need to generate new force field. That is one reason why I'm here. And also, we just got a force field for this sodium 2, nickel 2, telluride 06. This is next generation sodium battery materials. We have a DFT results that is just published in organic chemistry, but we want to do molecular dynamic simulations for diffusivity and conductivities and so on. And my PhD student is doing summer internship at Sandia. So as soon as she's back, we're gonna work on that one. And we also start developing the force field for uranium compound with a fusion product. And this is a little bit more tricky. So I'd like to talk to you about, what you advise us to look at. And I'd like to thank my hardworking students and postdocs, and my collaborators, and Dr. Bandwin for force field, and NASA Grand Center for oversighting, and then also this work is funded by NASA. Thank you for your attention.
Questions for Nujah?
Hi, very nice talk, thank you. And do you consider PBC in your pooling simulation?
Oh, can you
PBC,
speak a-
periodic boundary condition,
Yes, we are applying periodic boundary condition, of course.
in X and Y direction, right?
X, Y, Z.
X, Y, Z?
Mhm.
Okay, thank you so much.
Okay, sure.
Hi, ma'am. I just wanted to know, like, what is the reason of using ReaxFF for modeling? Like, is there any particular study with respect to bond breaking is intended in coming time?
There is a bond breaking, mechanism, of course, friction, right? Sliding motion. But the main reason is the force field. That's the best force field we got. My second postdoc tried to use Buckingham force field. But when we did the lattice constants are okay, but when he did Raman IR calculations, they are shifted, big time. So that happened to be not the right one.
Okay, for the sake of time, let's thank our speaker again and move on.
Thank you.
He's unsure.
We have one more talk before a break where coffee and water will be served out in the lobby, which our talk will be from Katsumi Hagita, who will be talking to us about coarse-grained molecular dynamic simulations.
Thank you, Chairman. My name is Katsumi Hagita from National Defense Academy of Japan. This slide is cut. We need time to control this slide.
Zoomed in.
Okay. I use the sharing the screen. It's okay. Oh,
Zoomed in. Can you share? Oh, this.
sorry.
So now, go switch.
Okay.
And I'll close this.
This one.
No, don't do anything. So press the button.
Sure. This one. It's okay. Oh. Okay. Reduce the display resolution. Yeah, okay. I reduce the resolution. Okay. Is it fine? Okay, yes. I'm sorry to time to control my display. So today I'd like to talk about large-scale CGMD simulation to evaluate the two-dimensional scattering pattern of straight polymer materials. So, okay, this is the introduction of the polymer materials. Polymer materials, as known, the soft materials such as rubbers, gels, and resins. This material consists with long polymer chain like this. It consists from the carbon chains. So this is a coarse-grained model, and this is the united atom model. This is a all atom model. So our interest is the polymer physics and statistical physics and the computational physics and high performance computing. Key point of our interest is the entanglements and networks. For example, network polymer is presented like this. Straight polymer chains tend to the direction of the crystal axis. We can get the controlled crystallization in the polyethylene films. this type of network is related to the hydrogel. It is an application for the medical or some ones. Another application is a nanoparticle field system. It's various industrial products, tire, films, and automotive parties. Here, we appreciate the productivity that come with using the lamps. This cover art, this selected cover art is a recent of our works using the lamps. Very thanks to lamps. So here, today's main topic is the two-dimensional scattering patterns. Two-dimensional scattering pattern is observed in the synchrotron facility or Labo Sachs machine. So we observe the cross-section of QZ equals 0 of three-dimensional scattering structure factor like this. It obtained from the 3D Fourier transformation of the density fields. In the small angle region, we can observe the structural information of mesoscale structures such as typically 100 or 1 micrometers. On the other hand, wide angle scattering pattern observes the atomic structural information, typically 0.1 to 1 nanometer scale. So here we want to evaluate the 2D SPs. We have some troubles in the statistics due to the small system size. Here we use the improvement of statistics using the circular average in the uniaxial asymmetric systems, such as uniaxial elongation or flow or someone. So this is a technique in the computation only. Here we want to introduce the two polymer models. First is a polyethylene crystallization model. And second is a gel networks. Sorry, gel, not get. Here, first model is a polyethylene crystal. In this model, we should maintain the carbon backbone to reproduce the spontaneous crystallization phenomena. And to improve the computing speed, we ignore the hydrogen atoms and ignore the charge. Thus, we use the united atom force field. And here we use the trap UA force field because trap UA force field has a high reproducibility compared to the other general united atom force fields. In the second model, the gel networks, we use the Grest-Kramer force field. It consists of the Lennard-Jones pair potentials and Fene bond potentials. In addition, we recently developed the bond breakage model to fit with the Grest-Kramer force field curve at low elongation strain. This is one of a movie to demonstrate the spontaneous crystallization of polyethylene long chains. We can see the self-foldings like this. This melt is not pure melt, it's pre-stretched melt. Due to the direction of the pre-stretch, we can get the crystal structure in this right direction. We found long polyethylene chain can make the spontaneous crystallization domain. So recently, we revised this model in point of view of the force field. In this case, we use the Dryden force field. This force field is not high quality. Recently, we use the trap force field to improve the quality of as a material computation experiment. In recent our simulation, we reproduced the heat pre-stretch experiment. First is the pre-stretch elongation to apply the strain memory. In simulation is the same procedure. We apply the pre-elongation, and second step perform the NPT simulation for the crystallization. In this simulation, we use the 16 mega united atom particles. it's a large system. The phosphorylated trap UA. This is the size of the periodic boundary conditions. We spend many computation time by using 64,800 GPUs, 1.5 months, 5 microsecond. This computation is using the GLOMAX. But this applying strain and observation of the SS curves and fracture experiment were performed using the LAMMPS. This is one of the result. We need 5,000 nanosec to achieve the crystallinity comparable to the experiment. This is one of the snapshot of the crystallized domains. This is a scattering pattern evaluated from our large-scale MD simulation and corresponding experiments. We have the good corresponding between the MD simulations and experiments. Thus, we can consider our procedure can be regarded as a digital twin because the 2DSP and stress strain curves is matched to the experiment between the simulation and the experiment. This is a stress strain curve in this simulation. This is similar to the experiment. Thus, now we are performing the detailed molecular level analysis. For example, to topological analysis in the nucleation stage and crystal growth stage, and etc. This is the first topic. This is the second topic. Second topic is the storage gel networks. In gel networks, increase the inhomogeneity with the stretching. Weaker part are more stretched partially. Thus, we can observe the abnormal butterfly pattern in the smaller angle regions. Here, we also consider the bond breakage model, enhancing the inhomogeneity. The weak bond will be cut due to the bond breakage model. So, this is the benefit of the bond breakage model. We can evaluate the natural stress strain curve and the fracture energy estimation. This is a SS curve with the bond breakage model. We can see the like this curve. Thus, we can evaluate the fracture energy as the from the area of this part. On the other hand, without the bond breakage model, so stress was increasing with strains, not fracture behavior because unbreakable bond. Thus, we cannot evaluate the area and fracture energies. Thus, we recommend to use this one in the case to consider both of SS curve and fracture energy estimation. Here we introduce the abnormal butterfly pattern in the gel experiments. A typical picture of the abnormal butterfly pattern. In the abnormal butterfly pattern, we can observe the bright peak on the Q-axis parallel to the stretch direction. This is the stretch direction. This is a bright peak of abnormal butterfly pattern. Second feature of abnormal butterfly pattern is dark streak on the Q-axis perpendicular. Like this. This is negative correlation. On the other hand, we must introduce the normal butterfly pattern. Normal butterfly pattern comes from the affine-like deformation. So because that we can observe the bright peak on the Q-axis perpendicular to the stretch direction, like this. In the Gary system, ABP was observed as the small angle region because, thus larger system size required for the smaller angle regions. Thus, we need the high performance computing and LAMMPS. So recently, we used the FUGAC supercomputer. This is the last massive CPU parallelized supercomputer. We consider that large atom size as a polymer system. challenging size using full node of the FUGAC system is 3 billion particles, but productive run performed in the 13 megaparticles. This size is used in our recent publication. Towards challenge size, this size, we now try to improve some code. So first point is MPI open MP hybrid parallelization is required because due to the memory limitation by the MPI library in the FUGAC. This is a problem in FUGAC. We use a 3 OMP and 60 MPI process per node. Second, we tune the processor command with the 2 level, and we perform the source code change. So improve source code LAMMPS, fix range one. We apply the random number generator with a Mersenne twister and OMP parallelization for random number generators. So this is a simulation parameter and snapshot. Here we base network with the diamond lattice. Average strand length is 25, about 25. It means 25 beads between the neighboring cross links of diamond lattice-like network. Here we introduce a simple inhomogeneity with bimodal strand lengths like this. And number of density is set like Gales 0.1. In the case of rubber case, this number of density is 0.85. Snapshot of crossing point like this, we can see the inhomogeneity increase for the larger strain like this. This snapshot is very fuzzy, but scattering pattern is clear evidence of this behavior. We can get the every peak position seems to be shifted larger strain like this, and more detailed analysis like this is drawn in the our published paper. So this is a conclusion by my talk. LAMMPS enable the large-scale simulation of the polymer material system to show the mesoscale behavior observed two-dimensional scattering pattern in the scattering experiment. That we confirm the reproducibility and origin and the details of behavior of abnormal butterfly patterns. So last, I want to say that we need to advise to use the LAMMPS with HPCs. Thank you.
Thank you. Questions for the speaker? I have a quick question then. How are you doing your analysis on these large simulations, the billion particle systems? Are there tools in LAMMPS that you're using or have to write your own analysis tools?
So we use recent analysis use Python or own C or Fortran code.
I guess there are no more questions unless there are some online. Okay. Okay, let's thank our speaker again.
Thank you.
Okay, so I have failed us slightly, a lot on keeping on schedule. And unfortunately, our next speaker has a time constraint. So if you do want to run into the lobby and grab a coffee or something and bring it back, you can still do that. But we're going to have the next speaker start with us right away because of her schedules being compressed. Mary Alice, if you're online, can you please start sharing?
Yeah, can you hear me, Mitch?
Yep, that's loud and clear.
Okay, perfect. Let me see here. Okay. Yeah, thanks for being flexible. Let's see. Can you see my slides?
Yes.
Okay. Let me put them in presentation mode if I can find it. There it is. Okay.
Our next speaker is Mary Alice Cosentino from Sandia Labs, who has been playing a large role in our potential development activities locally, but is also contributing a lot of her work back to the fusion materials world and really making great headway in that area. So hopefully we're going to hear a lot more about that in this talk.
Yeah, thanks, Mitch, for the introduction. So yeah, I'm Mary Alice Cosentino, and today I'm going to talk about our work here on atomistic modeling of materials for fusion energy using the machine learning interatomic potentials that we're developing here at Sandia. Oops. Let's see. Okay, there you go. First, I just want to thank all my collaborators and the session organizers for allowing me to present this work. So I have a lot of folks over at Sandia and that are working on all this potential development work. And then experimental colleagues at University of New Mexico and University of California and University of Tennessee that are helping us benchmark these potentials. And then I'm working with folks over at Stony Brook University on one of the projects that I'll talk about today. So thanks to all the folks that are helping on all these different projects. So I'm going to give a brief introduction on materials for fusion energy and kind of the challenges that we're facing in terms of developing materials for these really extreme environments that are present in the reactor. So as you can imagine, it's very difficult to develop materials to handle the really extreme conditions that are experienced within the tokamak fusion reactors. And so you can imagine you're basically trying to take the sun and put it in a box made of earthly materials. And it turns out that's a pretty challenging problem to overcome. So we're dealing with really high heat loads on the order of 10 to 20 megawatts per meter squared in sort of a sustained mode. And these can get much higher during off-normal events within the reactor. And then we're also dealing with high particle fluxes on the order of 10 to the 24th per meter squared per second of different ion species, mostly the plasma, which is the hydrogen, and then the helium byproduct, but then impurities that get into the plasma from other parts of the reactor. And so you can kind of see the inside of one of these things here. The key thing is this diverter region. This component within the reactor is going to be exposed to the most damage within the reactor. And so that's kind of where a lot of the focus is in developing the armor for this component. And so tungsten is currently our candidate diverter material. It has a lot of really nice thermal properties and it's resistant to, say, sputtering from these plasma species that are coming in. But even tungsten has some issues with it. For example, at the really high hydrogen fluences that we're seeing in these reactors, you get these hydrogen blisters that can form. You get helium fuzz growth on the surface. These are these nano-sized tendrils that form under very fusion-specific conditions, and this can degrade the properties of the tungsten diverter. And then you get things like intermetallics or other, chemical species that are forming on the surface from these other impurities that are present in the plasma. And so we want to understand how all this is happening and what's driving these, experimentally observed degradation phenomena so that we can try to design better diverter materials. The thing is that a lot of these initial processes that are driving what we see in the experiments are actually happening at an atomistic scale. So for example, you can get these plasma species that can come in and hit the surface. They can sputter atoms off the surface. You can get fuel species that implant and create defects in the material. You can get accumulation of things like helium, which forms bubbles in the material and then starts degrading the near surface region. And so we want to understand these processes, and it turns out that molecular dynamics is really well suited for studying a lot of this initial phenomena that's sort of driving this macroscopic degradation that we see in the reactor. So now we move on to the point of why do we need machine learning interatomic potentials? Well, as we want to model these really complex systems in chemistry, getting to be studying things like codeposits that form on the surface, but these are, not simple, structures that have a lot of different species in there. And, you're modeling things at very high temperatures and at very, high energies and things like that. And we want to use molecular dynamics, of course, to study this. So we need really robust interatomic potentials to kind of capture the complex chemistry and physics that's happening at these interfaces. So on the one hand, in terms of atomic structure methods, you have electronic structure methods, which are very accurate, and you can do a lot of really relevant physics, especially looking at like defect energetics and things like that. But they're very expensive, so you can really only model about 100 atoms at a time. So you're not really going to get to a lot of the really dynamic processes that we're interested in studying. And then we have, of course, MD with classical potentials. There's a lot of really great functional forms that are good for a lot of different systems, and it scales much better, where you're getting to billions of atoms that you can simulate on modern supercomputers. Of course, the accuracy is highly dependent on the potential and the application the potentials are fit for. So when you're going to these extreme conditions where you have a lot of different species present, where you're having a lot of different very far from equilibrium structures that are forming. Sometimes these classical potentials can fail, and you can kind of be limited in the types of physics that you can model. So with the machine learned interatomic potentials, the idea is kind of to get the best of both worlds, where you can train these models to data from the electronic structure method, but then run them in MD. So the idea is that you have the quantum accuracy from the electronic structure methods, but then the scalability with the MD simulations. And they can be more flexible because they're not tied to some functional form like the classical potentials are. But it's a little bit of a double-edged sword. So you have to have really good training data and methods for fitting your potentials to sort of constrain the models so that they don't give you, crazy responses, which can sometimes be a challenge. So what makes up these machine learned interatomic potentials? So the first thing is the training data, which, in my opinion, is one of the most important parts of these models. Is you need really good training data. And so you generate this using some sort of quantum method. Usually we use things like DFT, and you have a lot of different structures that have energies, forces, and stresses associated with each configuration of atom. And you want to have a lot of sampling of, the potential energy surface that's present for these different species you're trying to model. So you want things like, bulk structures, liquids, defects, surfaces, and maybe some specific configurations for the types of things you want to simulate. So for me, modeling these plasma material interactions, I'm really interested in defects. That's kind of what's driving all this damage that's happening in sort of these nuclear environments. And then, of course, you need a method to then take those structures and then link them to an energy and force, and that's done using the descriptor. So the descriptor basically tells you, is a mathematical formulation of what the structure of whatever, the atomic structure of your different configurations, and then that gets linked to an energy. You can kind of think of it as a fingerprint of the local environment. So, if you have a defect here, or if you have a surface, these descriptors will then change, and that manifests in a change in the energy and forces for the potential. And of course, they have to have certain qualities like being, rotation, translation, permeation, variant, and all these things. Some examples are shown here. So the bispectrum, SOAP, ACE, moment tensors. There's a bunch of different flavors of descriptors out there these days. And then lastly, you need a regression method to sort of parameterize your model. And so this can be as simple as linear regression or as complex as a neural network. And so for the work that I'm going to show here today, we've been using ACE descriptors. This is like atomic cluster expansion descriptors. And we are typically fitting to energies, forces, and stresses calculated from DFT. And we typically use linear regression, as we found this kind of makes things a little bit more stable. So here's sort of how this works in practice. So here's the model form for the ACE descriptors. So you can see the energy is basically a summation of these different body order terms. And that's kind of the nice part about ACE, is that you can include more or less of these different body terms, for example. So if you really want to emphasize 2 or 3 body terms, you can include more descriptors in that particular category, or you can include higher order terms if your system needs it. And so it's very generalizable and flexible in that way, which is really nice. And then in terms of the regression method, again, we're just doing some simple linear regression where we are basically trying to minimize what's in the training data, which is this big T here for the energies and forces, and then what the potential is predicting for those same energies and forces of all the different configurations. The way this works in practice is shown on the right hand here. So this is sort of our development workflow for these potentials. And so we first generate a large set of DFT reference data. This can be anywhere from a few thousand to tens of thousands of configurations. And then we use our FitSnap code, which is available here at GitHub. So if you're interested in testing it out, you can go check it out there. There's a couple of examples that you can try out for the different descriptors and methods we have. But basically, FitSnap will take your DFT reference data and do all the linear regression or neural network or whatever you want to use to develop a potential. The thing is that there's some parameters that need to be set. So we have 2 different candidate types of parameters. The first one are things called what we call hyperparameters. These are parameters that explicitly will change the descriptors themselves. So these are things like radial cutoffs or some of the parameters in the ACE description, for example. And then we have group weights, and the group weights are weights on the training data. So you can organize your training data different ways. So if you want to emphasize particular parts of your training set, you can do that during the linear regression. And that's where this W here on the left-hand side comes from in the regression method. So if you really care about getting surfaces, for example, you can weight those structures more so in the linear regression. And so to optimize these parameters, we use a sort of an outer loop. This is the Dakota software that basically will do a genetic algorithm to give you some candidate set of parameters, and then we generate a potential, and then we evaluate that potential on a set of objective functions. So these can be things like energy and force errors or material properties. So we can directly fit the potentials to, say, like a cohesive energy or an elastic constant or something like that. And then typically we find sometimes when it'll look good, calculating these 0K properties, but then when you run dynamics, you get some weird structures forming. So we kind of sometimes will, in a sort of by hand way, throw in extra training data back into the training set to, prohibit any bad behavior that we see with these potentials after we have fit them. So it's kind of a bit of an iterative process as we're developing these potentials. All right. Okay, so I'm going to highlight a bit of the past work that we've done. So I'm not going to go into details about this work because I presented this, elsewhere at, other conferences and probably at the prior LAMMPS workshop. So, but we've developed initially a bunch of SNAP potentials. So similar to ACE, but the descriptors are only 4-body descriptors. So Mitch originally had generated this tungsten beryllium potential, which we then had gone on to study these like intermetallics that they see observed in the experimental work, and we were actually able to see and quantify sort of the initial stage of how these intermetallics form on the surface, which was really important to understand, how this tungsten material was being degraded. And then we took this a step further and added helium in there and found that when you have these intermetallic layers on the surface, it actually prevented helium bubbles from forming, which is actually a good thing because we don't want helium bubbles forming in the material because they tend to degrade the mechanical properties and cause a lot of problems in the tungsten. And then along with Mitch and Aiden and Meg and Ember, we developed this tungsten hydrogen potential, and we found that we saw these 2D platelet-like structures forming at a very high hydrogen fluences, and Ember did some DFT work and found that these were actually stable structures in DFT. So this could be a mechanism for hydrogen retention in these materials and potentially precursors to blisters that form in the material. And then lastly, Ember Sikorsky again, or Salas, I guess, is developed a tungsten zirconium carbide potential, and this is one of these like advanced candidate materials for the diverter region. The zirconium carbide helps to stabilize the tungsten and prevent recrystallization and improve some of the mechanical properties. And she developed this really nice potential where we were actually able to study how the interface between these two materials changes as a function of temperature. So the most stable interface actually changes depending on if you're at 0K or at 2500K, which will then, which is kind of how hot these materials can get as you have, an off-normal event, for example. So we weren't able to see this in DFT because you can only really do the 0K. So we were able to see how the interface stability changes as a function of temperature, and this was due to carbon diffusion at the interface. Right, so this is kind of, again, highlights of all the prior work that we've been doing. And so the rest of this talk is going to be split into 2 parts. The first is some work I've been doing on a SIDAC project to look at transmutation elements. And then the second part's based on LDRT that was looking at tungsten-based multi-component alloys for fusion energy. And so I'll get into the next part of the talk. So this is all work that's being done on a fusion energy science SIDAC project, where we are looking at transmutation products in these first wall materials. And so again, we're studying these diverter and first wall materials that are subject to extreme conditions. And when you're operating in a neutron environment, those neutrons will actually change whatever material you initially have in those wall materials to something else due to neutron absorption and then radioactive decay, basically. And so as a function of time, the chemistry of your material is actually going to change, and this is going to change the how your material is going to behave in the reactor. And so we need to understand that in order to be able to predict how these components degrade. And so the first wall design sort of materials that we're looking at are shown here. So we have tungsten as the first the armor for this diverter region. And then we have RAFM steel as the structural material. And then we have this silicon carbide here as like a barrier between some of the molten salt that we're using in the reactor for basically breeding more tritium. And here's an example of some of these transmutation products that can occur. So here's the decay or the transmutation products for tungsten. So you can see the black line here is the tungsten material, which is fairly flat, but then as a function of irradiation time, and this is in years, you start getting, non-trivial amounts of rhenium, osmium, tantalum, particularly in the tungsten. So it's transmuting into rhenium and osmium in particular. And so we want to understand how this impacts thermomechanical properties and defect properties. And so, especially since we don't have an actual fusion neutron source right now, we don't have any experiments that directly simulate the energy spectrum that we get. These types of modeling and simulation work is really important to do so we can understand how these transmutation products affect the first wall materials. And so again, we want to do a lot of stuff with MD, and we're doing it for these three material systems. So tungsten with rhenium osmium as the transmutation products, iron chrome as our steel with manganese as the transmutation product, and then the magnesium and the silicon carbide. And so today I'm just going to talk about the tungsten rhenium part of the potential. And so again, these are the main transmutation products in tungsten. The issue is that rhenium will cluster and form precipitates in tungsten, especially when you're operating in a neutron environment where you have defects, you have vacancies. These rhenium atoms will precipitate in this type of environment. And this actually detrimentally affects sort of the mechanical properties of tungsten. So the current potentials right now don't predict the correct rhenium-rhenium interactions. What they see in DFT, you particularly focusing on this red and blue curves down here, is that rhenium has a repulsive interaction. So it really should only cluster when you have vacancies present. And so that's what we really want to study, is the effect of the interatomic potential on this rhenium clustering phenomena, especially when you can get this particular physics correct. So we're really focused on trying to reproduce these rhenium binding energies, as well as just generally getting thermomechanical properties correct. So for this tungsten rhenium training set, I focus a lot on doing just, the pure phases, looking at elastically strained, sheared, and compressed unit cells. This helps to sample sort of the potential energy surface really well. We have a lot of different defect configurations, whether it's point defects, rhenium in there, or rhenium vacancies. And then we also included the intermetallic. So there's two different phases of the tungsten rhenium intermetallic. And so we have structures that represent the different filling of these different positions within the intermetallic phases. And then, of course, DFT-MD at high temperatures, which really helps to sample these potential energy surfaces. And so there's something around 1,300 configurations in the tungsten rhenium training set. For the pure phases, this is, sort of subset of like deformed unit cells, DFT-MD, surfaces, dimers, and defects tends to really sample the potential energy surface really well, so that you can generally have something like this that will get you, cohesive energies and elastic constants and defect formation energies for these materials pretty easily with ACE. And then the sort of alloy potential, which is the full tungsten rhenium potential, we included, just additional similar structures, especially these defects and intermetallics and things like that. So in terms of fitting, we have a set of parameters. So we have the radial cutoffs for each of the elements and the cross terms. So that makes 3 different radial cutoffs. We have an inner cutoff for where the ACE kind of gets damped down to 0. And this is tied to sort of where we have our ZBL potential. So the ZBL potential is a hard wall, completely repulsive potential, which is often used in the radiation damage community to make sure that when you have these high energy neutron simulations, you don't have atoms that are overlapping or getting too close to each other. So it makes sure that you have a really strong repulsive interaction at short interatomic separations. And then there's this lambda term in the ACE formulation, and this basically emphasizes how much sort of short-range interactions are important. And so you can kind of tune this and it'll help to either improve, help to improve the performance of the potential. And then of course we have the energy and force group weights for the linear regression. So if you were to try to fit this whole thing at once, it's a lot of parameters. It's probably something like 40 or 45 parameters. So we found a way where we kind of just optimize the single element potentials and then freeze parameters and then do the full fit, which seems to work pretty well from what I've seen. So basically, for example, you'll fit the tungsten potential. For tungsten, I care about getting, elastic constants, cohesive energies, and the defect and migration energies for the tungsten self-interstitial and vacancy defects. And then you have just the, cutoffs, the lambdas, and then the group weights for this, which is something like maybe 15 or 16 parameters, 15 to 20, let's say. And then for rhenium, because we're not actually modeling rhenium, we just care about rhenium being in the tungsten. I just want to get elastic constants and cohesive energies just to make sure the energy is sort of in the right ballpark for modeling this particular element. And of course, you have the same set of parameters here. And then eventually, so we fit these things separately, and then freeze all these different parameters and then put it into the final tungsten rhenium fit, where we add in 3 different extra sort of target properties, which are the defect energies, the migration barriers, and the binding energies for the mixed tungsten rhenium structures. And so then you have a set of parameters there. And so, for example, we do these things. Here's an example of just a pure tungsten fit. You can see just the elastic constants here, for example, that are pretty much in the ballpark. Same for the rhenium ones. And then we freeze these parameters and you still get pretty much the same, more or less, performance here for the full fit. So by doing this sort of not these sort of stacked way of doing the single fits and then the full fits, you kind of help to reduce the number of parameters and still have the same more or less accuracy when you do the entire alloy fit. And so for the initial tungsten rhenium potential, here's just, I'm going to throw up a bunch of tables, so I'm really sorry. It's a lot of information, but basically we fit to elastic constants. They're shown here. Cohesive energies, again, we're pretty much reproducing the tungsten rhenium structures. Here's the defect formation energies, which are pretty well reproduced. Some of the dumbbells are a little bit below what the DFT is predicting, but what we really care about is getting the ordering correct because we want that 1-1-1 dumbbell to be the most stable configuration. So that's pretty good. And then migration barriers look pretty well. The vacancy one is always a little bit high in general, but the self-interstitial and the rhenium vacancy migration barriers look pretty good. And most importantly, we're trying to get these rhenium binding energies correct. And so this is the DFT shown in the orange here, and then the ACE is shown in green. So we're actually really nailing these binding energies, which is kind of what was the goal of this, was to reproduce this so that we can do some studies. So then we did some initial testing. Of course, there's always issues with this thing. So it's kind of a lessons learned type of situation. But basically, we ran like a 5K EV pKa simulation. I'll show that here. This is where you have a cascade. We're simulating as if a neutron came in and it creates a bunch of defects, which then quenches back down. And you can see the rhenium atoms moving again. So I can play this again. But basically, this is really stable, which is great because this is a kind of a test of the potential. The issue is that my colleagues at Stony Brook University were starting to run some MCMD simulations. And what they found was that at low temperatures, you get this ordered phase that starts to form with the rhenium atoms that really wasn't predicted by DFT. And the other issues, they didn't really see the rhenium going into the vacancies. So what they found was that the rhenium vacancy binding energy in terms of the second and third nearest neighbor were too low. And then this ordered phase was due to a positive rhenium binding energy. And so what we found was that this second nearest neighbor binding energy was too high. So the ACE is shown in green and the DFT is shown in orange. And so what happened is that the ACE basically predicted a positive energy for the second nearest neighbor binding energy, which was driving this ordered phase that they were observing in the simulations. And so we of course, I decided to go back and fix this so that they didn't have to deal with this ordered phase forming in their MCMD simulations. And so what happened was we refit the potential. I threw in a couple extra structures in there for these rhenium binding energies. These are like, 2 rhenium atoms at different nearest neighbor distances from each other. And then I added in a new objective function. So I actually targeted these nearest neighbor binding energies and then also this rhenium vacancy binding energy as part of the fit. And so we ended up refitting the ACE potential. Again, apologies for all the tables here, but here's the, the elastic constant. Some of these are not quite as good as before. So you can see this, the C11's a little bit low, the C12 is a little bit high, but cohesive energies are more or less the same. The defect formation energies are kind of the same, except for this negative one for the rhenium substitutional energy. Migration energies look pretty good. Oh yeah, here's the energy and force areas in case you were curious. And then now if we look at this nearest neighbor binding energy, the ACE, which is again in green here, is all below 0, which is what we want. So that should help with their ordered phases that they're observing. And then the rhenium vacancy binding energies are all positive. And so basically what we found is that, going back and adding the structures and then tweaking sort of the fitting of the potential, we were able to kind of fix these problems that we were observing. So my colleagues right now are rerunning these simulations so that we can hopefully see if it changed the results. So that's kind of a work in progress right now. But this is sort of the process that we go through to develop these potentials. All right, so the second part of this is going to focus on developing advanced tungsten materials. So I've been talking about tungsten a lot and how great it is, but there's actually a lot of problems with tungsten in terms of its role as a first water material. On the high temperature end, it suffers from a high ductile to brittle transition temperature, and then also a low recrystallization temperature. And this kind of limits the operating window for tungsten in the reactor and can cause problems. So we need to look at other diverter materials, but they need to balance, of course, a bunch of properties, as I've said. So we want to get sort of improvement in the mechanical behavior of tungsten while still maintaining sort of the good thermal and sort of radiation and deuterium properties of tungsten. And so we're looking at advanced alloys here. So a lot of prior experimental and modeling work has showed that alloying tungsten with other elements can increase a lot of the strength and mechanical properties, but then we don't know necessarily how these materials are going to behave in terms of like the radiation effects in the material. So here's, especially as you go to more and more sort of complex chemistry in the alloy, you can really reduce, for example, the helium bubble size. So there's been a lot of experimental works looking at these high entropy alloys. And you can see sort of the low entropy alloys, the medium, and then the high, and you can see how for example, the helium bubble sizes decrease as you increase the complexity of the alloy. And so what we really want to look at is how could you potentially optimize the alloy composition of these materials for improving radiation tolerance and other properties of the alloy when you have a really vast parameter space to search over. And so the idea,
just 2 more minutes.
yes.
Good.
Oh, I have 2 minutes. Okay. Well, I will just maybe skip a lot of this stuff. So basically what we did is we sampled a bunch of different alloy chemistries using MD to look for favorable properties. And so we're trying to use MD to accelerate sort of the discovery of these different materials. What we found is that for this particular part of this presentation, we're looking at helium bubbles and how the size of the helium bubble was affected by the alloy composition. And we found that it was in fact very, very much changed as a function of the alloy composition. So basically, as you change, the moral of the story here is that increasing moly basically gives you less volume in the material, which resulted in smaller cluster sizes. So moly tended to decrease the ability of the helium to move in the material, so it couldn't cluster. It decreased the volume, so you couldn't grow bubbles as large. Niobium had the opposite effect. So what we found was that you could use the initial interstitial atomic volume of the alloy to then predict long-term behavior of the material. So I'll kind of skip this basically. And that was the moral of the story here. We actually tested some of these alloys under some plasma conditions. This was done at UCSD at the Pisces experiment. And basically our colleagues at UNM tested these materials. You can see here where you have, enrichment in moly versus in this A area here versus enrichment in tantalum or niobium, you actually change the amount of damage that's happening in the material. And so what they found was that you actually get local changes in these structures. So these are these fuzzy structures I talked about on that first slide. So we actually see enrichment in particular elements. So you get a lot of tantalum in there, but not a lot of moly or niobium in these tendril regions. So the chemistry is non-uniform in these materials, which is kind of interesting as a function of the fluence. But basically, the cool thing that we saw is that we simulated these same materials, and we found that the bubble sizes between the experiments and the MD were actually similar. So in this particular niobium tantalum moly versus niobium tantalum titanium alloy, we had larger bubbles in this one on the right here, about a factor of 2 in the experiments, and we see the same thing in MD. So we're actually predicting these materials, and I forgot to mention these are machine learned interatomic potentials. So we're actually getting some good comparison with experiments. And basically what we found was that the experimental bubble size plotted as a function of the migration barrier of the helium actually correlates really well. We can see that as the migration barrier increases, it results in a suppression of helium bubble growth in the material. And so that was pretty cool that we were able to get some correlation between the MD and then the experimental size. So sorry, I flipped through that very quickly, but basically that's the end of my talk now. But basically we're developing a bunch of potentials to study plasma-facing materials. Of course, there's a lot of work still to be done to, develop more advanced potentials for these different materials and start adding in like hydrogen, helium, and things like that in them. So I'll stop there and take any questions if there's time, but thanks for your attention. I appreciate it.
Okay. We'll do one question online while the people in the room come to the microphone. From Eduardo Bringa, he would like to know how the ZBL switching was done and why not just sample configurations at close range in your training set?
Yeah, that's a good question. So one, DFT is not always great at doing those short separation distances, and you really need to get to like very close atomic separation because it's hard to restrain the potential from basically dipping. A lot of times it'll look like it's repulsive and then it starts turning over to really low potential energies at short atomic separations. So the ZBL pretty much guarantees that, and you don't have to like try to force the ACE potential to reproduce sort of that difficult space to represent in DFT and for the potential. And the switching function is done. It's just, we use like the hybrid overlay potential style in LAMMPS. And so there's that built-in switching function. I forget what it is off the top of my head, but you define an inner and outer radial cutoff for that. And that then slowly switches to 0 automatically for the ZBL potential. It's already built into LAMMPS. So we rely on that.
Okay, we have one more question in the room.
Thank you, Mary, for the great talk. Very interesting. I have a very generic question. So in your talk, and it seems like in general in the community developing MLIAPs in the labs, you've settled on descriptor-based methods as opposed to graph-based methods. Can you comment on that? Especially since I've, as a non-expert, I've heard that the more elements you have, the more difficult descriptor-based methods become compared to graph-based methods. But clearly that's not a problem for you because you're doing alloys with a lot of elements.
Yeah, that's a good question. To be honest, I don't know that much about the graph style networks. Or the graph style potentials. I haven't done a lot of work in that area. But in terms of the descriptor methods, I mean, I think at some point we're going to run into issues, especially with ACE, because it's very the descriptors get to be very computationally expensive once you have more and more as you add more elements in there. I haven't run into accuracy issues quite yet. I think we're doing pretty well still with some of these descriptor methods in terms of getting these complex alloys, especially with this moly niobium tantalum titanium potential, which actually was a SNAP potential. I forgot to mention that, but we get some pretty good properties still, and we have a lot of experience built in with doing these kind of descriptor-based methods. So I think it's worth a try looking at some of these graph networks, especially if you want to look at like all the different plasma species interacting. That could maybe start getting to be too much for these descriptor methods. But so far it works, and so we keep using it. That's kind of my best answer there. But yeah, it's definitely something to look into. So I appreciate the comment there.
Thank you.
Okay, can we have any further questions be put in Slack? Mary Alice, if you could follow up there, that would be great.
Yes.
But we're going to close this session right now and take a 15-minute break, which means we'll be coming back at 11:15, where we'll do the rapid fire poster presentations up on the stage and then continue to the actual poster session after that. So 11:15, everyone. Aiden has one more announcement, though.
Thanks, Mitch. So my announcement is about lunch. We will have delicious sandwiches from Jimmy John's today for lunch. I think that's going to show up at 12 or 12:30, depending on how things go with the poster session.
Knock, knock.
Okay, that's great. Don't know how many we have, but yeah. All right, welcome back, everyone. We now have the lightning talks for the posters. So you can give a brief 1-minute pitch to try to get everyone to come look at your poster. If I could ask all the poster presenters to come up to this area and line up, preferably in approximately the order in which you're listed on the screen. And just for the format, so it is a 1-minute pitch. I will warn you at the 1 minute and, give you just a couple more seconds to finish up. And then, shortly after that, we'll try to kick you off the stage, right? So please keep your talk short. If you did not send a slide to Richard earlier, feel free to still line up here and we'll give you the same amount of time. Obviously, you just won't have a background. Yeah, if you have a poster, please come up and all right, so I'm looking forward to see everyone's pitch. If the first poster presentation can please go up there and get started. Okay. All right. Yeah. All right.
Hi, everyone. My name is Amrut Dyuti Swami. You can call me Amrut. I'm a PhD student from New Mexico Institute of Mining and Tech. And my poster is on impact of thermal gradient on interfacial energy and anisotropy in aluminum copper alloy. Primarily, I use MD and LAMMPS to simulate non-equilibrium solidification. In additive manufacturing, for aluminum copper alloys, we usually end up seeing a lot of defects, porosity, high thermal cracking, lack of fusion effects. Finding experimental causes for these is very difficult because of the high cooling and thermal gradient numbers. So we use MD to simulate conditions that happen during these rapid solidifications. We study the interface to find out why these happen and compute their magnitude for interfacial energy and its anisotropy. Primarily, I induce a thermal gradient across the solid melt interface and then study the interface by seeing its structure and also computing the energy and anisotropy terms from it. We then relate those terms to the magnitude of the thermal gradient and the physical insights into why those happen. Please come by my poster if you have any questions. I would love to discuss about these. Thank you.
Thanks a lot. Now have our next poster presenter.
Hi, I'm John Carnes from Lawrence Livermore National Lab, and my work is simulating polymer composites. Our system of interest is silicones with a silica filler. We're using a coarse-grained approach. The application is direct ink write 3D printing, and we're interested in capturing to a first approximation the surface modification of the silica filler particles. We're hoping to outrun an experimental campaign and get some information about different degradation modes as a function of the surface chemistry of those filler particles. And we did so by playing with the filler particle polymer interaction potentials. Thanks.
Thanks a lot.
Hi, I'm Joseph Raley. I'm a student from the University of Missouri Columbia, and I'm here presenting today on the molecular dynamic simulations I've run of the polymer polydimethylsiloxane. We've specifically studied the equilibrium properties and the shock response of the material under both explicit NVE simulations and Hugoniot-Stat approach using MSST. Yeah, if you're interested about that, come by my poster. Thank you.
Hi, good morning, everybody. So my name is Joshua Young, and I'm here with my colleague, Qingjie Li from LAMMPS. So our company's core technology offering is a universal machine learning interatomic potential called the preferred potential, or PFP, which is offered inside our cloud-based computing environment. So our poster details the newest release of this potential, version 8, which contains a highly structurally and chemically diverse training set of 60 million DFT calculations. And the new version also includes R2 scan functionality. So our potential covers 96 elements on the periodic table and 70 for the R2 scan functionality. So we have hundreds of users, both industry and academic, using our software. And so we featured on our poster a number of case studies, including users doing molecular dynamic simulations. So ranging from a variety of applications, including organic liquids, phase transitions in ceramics like ferroelectric barium titanate, delithiation in a battery cathode material, etc. So if you'd like to learn more about the potential, the training set, how it's trained, all of these types of things, please feel free to stop by the poster. Thank you.
Hello, everyone. My name is Rahul Verma. I'm a postdoc at NC State University. So this is the project which I started when I wanted to know how much data is sufficient to model a chemical reaction using a molecular dynamic simulation in machine learning, interatomic potential. So we developed a training workflow where we incorporated a potential energy exploration in between the AccuLearning protocol. So we developed a small software package to automate this process, and we applied this workflow to a system of a very small system, 1,3-butadiene cyclization reaction, where it goes from trans to cis rotation and then cyclobutene transformation. So we initially started with a very small 44 initial configuration. At the end of the workflow cycle, we end up with approximately 1,200 training configuration. And with that last frame of model, we ran the MLMD simulation to construct this free energy profile. So if you want to know more about the workflow, please visit the poster. Thank you.
Hello, my name is Sergio Romero. I'm part of the macro group, which is one of the research clusters that we had at Seagate Technologies. Unfortunately, we were short of one signature to get approval to present my poster. But if you bear with me, I'll be happy to talk to you about some of the stuff that we've been doing at Seagate, some of the opportunities that we had for collaboration, and if you're a grad student, some of the internship opportunities we have for PhD students. So just, I'll be there. Thank you.
All right. Hello, everyone. I'm Luke Cruz. I'm a postdoctoral student at the University of Missouri with Tommy. Today in my poster, I will discuss some of the work that we've been doing to explore and move towards these more accurate shock simulations of membranes. In particular, we'll emphasize molecular dynamic simulations of tip 3P water, and focus on how the commonly used practice of imposing these constraints, these holonomic constraints, influences shock state properties. In particular, how is the specific heat capacity and the Grunizing coefficient influence? If that sounds interesting to you at all, I'd love to field some questions. Thank you.
Hello, I'm Kohei Sasaki from Japan. Today, I present about the dielectric response and properties of polystyrene under the external electric field in post-session. We developed polymer materials to reduce energy loss of circuit for high-speed communication at gigahertz band. At gigahertz frequency, the dielectric loss is influenced by dipolar orientational polarization, which is corresponding to relaxational motion of atoms in polymers. In this study, we performed molecular dynamic simulations of polystyrene and the external electric field at 10 gigahertz. Polystyrene is a low dielectric loss model polymer, and it has stereoisomer and crystallinity. We investigate how the slight differences of polystyrene's chemical structure affect dielectric loss. If you have any information or advice in this research, please give me. Thank you.
Good morning, everyone. My name is Jiahu Yufang from University of South Carolina. Today, I'm here to share our work on polyamide membrane formation at the aqueous and organic interface. We simulated the cross-linking process of TMC and MPD monomers by using reactor protocols in LAMMPS. Our results show that there are two stages of this cross-linking process. At the first stage, monomers concentrate at the interface of water and hyacinth to achieve quick cross-linking. And at the second stage, as a pre-cross-link, the film develops, the cross-linking process will slow down but proceed. Our study shows that the interfacial fluctuation helps to maintain this continuous cross-linking at a slower second stage. Our simulated structure have good agreement with experimental measurement. That's all. Thanks for listening.
All right, that concludes our lightning talks. A lot of exciting work going on. So I'm looking to a lively poster session out in the lobby. So please meet these folks out there and let's talk about science.
One request for all the people with posters, please send, if you want, send me a digital copy of your poster so I can put it on the website. And yeah, maybe you reach more people.
Okay, welcome back from lunch, everybody. We're going to start the first breakout session in a moment here. And it's called a breakout, even though at this point we're still all together. I know you just ate lunch, but I want to just get a rough head count for dinner tonight. How many people are planning to go? This is El Pinto, which is a famous Mexican food or New Mexican food restaurant here in Albuquerque. Let's see what we got. Okay, so maybe 10, a dozen. That's great. What we'll probably, depending on what time we finish, which might be earlier than 5, depending on how much discussion there is in the last breakout session, which is about development topics or new features and ideas for LAMMPS. We might leave a little earlier, try to get to the restaurant before 6, if that's okay with everybody. So what we'll do, if like we have the last couple of days, is we'll all just gather in the lobby when we're done and we're ready to start getting ready to go to the restaurant. That way we can make sure people have rides and we cover everything. Okay, so we have a first breakout session, which I'll introduce now. Then the next hour, we're going to split into 3 groups. We're going to use this room and 2 rooms that are down near the lunchroom. We'll give you details on that. You can look on the website as well. And so we've got 3 different topics going at the same time. Depending on your interest, you can go to one of those. And then we'll meet back here for the last all together again for the developers breakout session. So our first one is from Ethan Holbrook and Juan Carlos Verduzco, if I pronounced that right, from Purdue. And they're going to tell us about the title up there about using AI with a large language model to try to get it to write decent LAMMPS input scripts. And I'll let them tell you what the agenda is for the next hour here.
Yeah, hi. So my name is Ethan Holbrook, and yeah, we're gonna talk about using LLMs. And this is
I'm Juan Verduzco, and I'm just interrupting Ethan to do a little announcement. Our workshop is going to have a hands-on activity sometime in the middle so that people can actually go and test it. So just a heads up so that if you need to charge your computer, you're going to need your computer. We're going to give you all the instructions, but just heads up, there's going to be an activity in the middle.
Yes, it's true. Okay, so I want to start off by reminding you of the talk that we had this morning by Professor Michael Klein about 8 decades of computational science. So we are also thinking about how computational science has been and where it's going. And we have this sort of simplified view where starting with Bernie Alder and Wainwright, doing the first MD to, as the field advanced throughout the years, generally custom MD codes were being built and largely people would publish a paper on a new code, like one paper, one code. And then in the 90s, we have the creation of LAMMPS that has really sort of unified a lot of different techniques for running MD and allows you to do a bunch of different things. And then moving forward, we're not quite there yet, but it seems like we might be moving towards a time of AI and automation where a lot of these the typical aspects of your workflow for running MD simulations are all built in one. And as we're like sort of evolving throughout this timeline, it has changed how the users are interacting with MD. So in the beginning, you were more of a specialist, and now you don't necessarily have to know the physics in depth to be able to run MD. And with the AI and automation, it might become more so that you can run useful and interesting experiments without the same level of knowledge, the same level of intimate knowledge of the code. So we want to talk about the process of writing a script. So still being in this third stage of interacting heavily with LAMMPS, we're thinking about what it takes to write a script. So generally, you need domain expertise. and you need to understand the physics that you want to simulate. So this involves the time scales that you're dealing with, the length scales, making sure that you're using a correct ensemble, having a potential that is suitable for your problem, and then manipulating your material or your system however best suits your problem. And then building on this foundation, you have to then design your experiment and accurately set up constraints. So in LAMMPS terms, this is stuff like boundary conditions, determining whether or not your system is periodic, specifying your neighbor list, how you want your data to be outputted, and then spatial definitions, so like regions or group definitions or stuff like that. So once you have all these things, you still can't quite run a LAMMPS experiment because you need to understand how the syntax works. You have to be able to implement the physics and the constraints that you understand in LAMMPS. So this is stuff like fix, run, time step, and knowing how to order your commands properly. And then the units are a pretty big part of this too, just making sure that you're in the right frame. So in talking to these software packages, these are, LAMMPS is a domain-specific language. And so the users will need a lot of experience with the syntax of the documentation to be able to run new and interesting simulations. So I have a little table here where I've broken it down into general purpose languages, which includes stuff like C or Python, and then scientific domain-specific languages. And so Python and C have things like compilers and linters, where you can determine if your script has some problems before runtime, not necessarily all. And then, but in LAMMPS, this is very manual. And similarly for the other two, your commands require strict ordering in most cases in LAMMPS. And then most of the time, when you have errors, the feedback comes in the form of a runtime crash. So with this in mind, JC is going to talk a little bit about how we are addressing this or looking to address this with large language models.
Yeah. So I don't think I have to introduce large language models to everybody here because you probably have seen them. You probably have used them today, I would guess. So large language models are these new kind of applications of transformer architectures that have popped up in the last decade. Most famously as the widespread release of ChatGPT a couple of years ago. And these large language models provide a lot of really impressive performance in natural language tasks. So these models are really good at question and answering, translation, summarization, and other tasks that in the 2010s were still areas of research on how to address. Large language models are really good at broad knowledge. They're few-shot learners. That means that if you give them an example, they can replicate the example and make something that looks correct. I'm going to talk a little bit about looks correct and is correct. So they are excellent NLP tasks. And the best kind of the most marketable thing that they have is that even when they're wrong, they are coherent. They're fluent in what they're saying. So large language models are, in a way, like a student that is very confident, but could still be wrong. So you can still be wrong. You can be confident and wrong. So this goes to the other part of large language models. They're prone to hallucinations. Hallucinations are basically made up facts that were not in the training set. It just, for the LLMs, it makes sense that it would be this way. Most of the commercial models still have some inaccessible information sources. So it's not like an LLM can go and run a simulation or an experiment. They rely on what other people have reported, which is notoriously hard for widespread commercial things to get. It's not like that ChatGPT can just go to Elsevier and get any paper that it wants. there are some boundaries there on copyright and a lot of ethical issues that I'm not going to address of how it gets information. The models that we're going to be using today also don't really line up what the training set was. It's a very obscure part of the LLM community that they don't really tell you what they were trained on, and you just have to trust that they know what they're talking about. They are somewhat bad at structured reasoning, that is making long-term plans. So if I want a simulation that requires several steps, it might not be able to stitch together which steps do you need to get the properties that you want. And in general, they're limited in task generalization. So these are very general models, as in they perform okay at many tasks. They're not great at specific tasks because they were not trained for them. So all of this introduction to large language models is to see, in our work, what we wanted to see is, can these LLMs be used to address the syntax problem of domain-specific languages? And here we're gonna spend a little bit of time on how do we kind of address some of these shortcomings of LLMs. And we're gonna do it through prompt engineering and some of the tools that Ethan described in the presentation yesterday. So prompt engineering, I'm gonna keep my analogy of a student. If you're giving, well, here I'm assuming that most people here have been instructors on a class or have been students in graduate school. So it's always easier for you to do your work when you get detailed instructions on what is required. So prompts are that version for an LLM. It's an instruction you provide to an LLM. So these instructions are really important. It's very important for you to give an LLM specific, logical, and clear prompts so that it can give you better answers. So it's more likely to give you a better performance. So if I were to say, write me a LAMMPS script for a simulation with atoms, I think most people here would not even know where to begin with that, because what do you want me to simulate? Like, there's not even like there's not a clear instruction of what you really want. It's missing a lot of context of what the task is and what the objective is gonna be. And it's overall very vague. So this is a bad prompt, don't use that prompt. A good prompt has a lot more details. So it includes things like system geometry and scale and materials and potentials that you want to use, which ensemble, which is the physics that Ethan was talking about. So you have to trust that you know the physics better than these models. So the more information you can give them about the physics, the better it is at kind of embedding those physics in its responses. So here I'm adding more things because it's a nanowire tensile strength, so loading conditions, and what outputs do you want. So you can see here in a very clear example how a bad prompt, it really does not help the LLM, and a good prompt at least gives it some context so that it can give you a better answer. So prompt engineering is a big field of basically professionals at asking these LLMs how to do things in a way that makes them better at doing the things. Because the phrasing of how you ask for things really has an impact on how they perform. So here I have a few strategies that have been kind of widespread adopted by the community on how to do prompt engineering. So here I'm gonna have a long prompt about asking for a LAMMPS script. And you can start with the first of the strategies, which is role-playing. So LLMs are basically models that predict which token, which word comes after the last one, which token is the most probable to come after the last one. So techniques like role-playing, where you tell the LLM that they are an expert at something, actually help. So if I say you're an expert at LAMMPS, it's gonna be better at things related to LAMMPS. And this could be related to the way that they're trained, that they can go and fetch things related to LAMMPS preemptively from their training, but role-playing is one of the strategies. The second one we already discussed a little bit is clear instructions. So your task is to generate complete runnable LAMMPS scripts based only on the details that I provided. So giving clear instructions, important for the prompt engineering. The third one is one of the most important ones, which is context awareness. So LAMMPS, as we all know, has different versions, maybe a stable release a year and a few in between. So you have to make sure that it knows what version of LAMMPS you have compiled, if you already have one compiled. You need to make sure that it's using the correct potentials with the correct names, and you needed to define all commands. In this case, you needed to define all commands, because there's a few commands that you can skip in LAMMPS that you shouldn't skip, but you can skip because they have default values. So LLMs, if they don't need it, they don't write it. They're always trying to save on tokens, so they're not going to generate things that you don't ask for. Another couple of strategies is providing examples. This is few shot training. This would be if you're asking for a LAMMPS script and you already have an example of a LAMMPS script that is similar, you can give it to the LLM so that the LLM kind of knows what it's looking like, what the output should look like. So you can provide examples and say, oh, I have these examples, but I want to do it for tungsten instead. And the last of the prompt engineering is step-by-step logic. So this goes to address the problem of long-term planning that large language models have. So if you ask it to, just like in the tutorials that we were doing in the first day, that you have the different sections in the LAMMPS script, like initialization and then system creation, then monitoring, which kind of helps you as a human understand how you're creating the script. For LLMs, you can also do that in text. So you can have these labeled sections and say, start with this, then do this, then do this, and generate each section by determining what commands belong in the section, how to use them, and ensuring that the syntax is correct. So this is all for vanilla LLMs, so just the commercial LLMs. In all of the examples that we're going to try today, we don't have a fine-tuned LLM. That is an LLM that has been specifically trained for LAMMPS. And we also don't have an LLM that is currently accessing the documentation directly. We are just relying on what the LLMs, commercial LLMs know. But these are future work that we're trying to explore, where we actually embed LAMMPS documentation into these LLMs to see how they perform. Mm-hmm.
So you're saying what you're going to show and what we're going to use today is knows none of this information that you just said.
Yes.
Would be useful to tell it.
Yes, so this is information that would be useful to tell. This here is how you would ask the question.
Right.
So this long text is how you would say, the instruction, write me a LAMMPS script, would have to include a few of these strategies too.
Okay, but we're not going to do that today because we're not set
No,
up.
so what I'm saying is the model itself has not been equipped with the direct LAMMPS documentation. So we're going to use these strategies to try to get the commercial LLM without the LAMMPS documentation directly to perform creating LAMMPS scripts.
So that was my second question. Why wouldn't ChatGPT or any one of these, why wouldn't it have read the LAMMPS documentation? Because it's just on the open web.
That's a great question as well. So they might have, but they do not tell us what the training set is. So they might have just scraped the documentation from the GitHub repo or from online, but we cannot be sure that they did, and we cannot be sure that they are actively using the commands as written in the documentation. That is something that you can add a posteriori to these models where they're trained the way that they're trained, and then you equip it with some tools to go and search for the command online to see what the compute does.
If I could add something real quick too. So one thing that we've noticed from just working with this is that a lot of times, there's a couple times we've generated scripts and we do this over and over with like the same prompt, and we ended up getting the same sort of command error. Like one of the specific examples was when doing a shock. It would add in a fake keyword called add that doesn't exist, and to my knowledge hasn't existed in LAMMPS. But on the forums for LAMMPS, there was a question where somebody mentioned using velocity add in their question. And so we think that the forums might be weighted a little bit more in the base models than some of the actual documentation.
Yeah, so the command that Ethan was describing was in velocity. So the LLMs were trying to do velocity add, and then just add the velocity. In LAMMPS, that would be velocity set, whatever velocity, sum yes. So you're summing that velocity to the current velocities that you have. the LLM was very sure that it was velocity at something. It could have been a LAMMPS command at some point, but we couldn't find that anywhere. It kind of makes sense that it would be phrased like that, just the way that the other velocity things work, but it's not the way that it's supposed to be. It was an interesting thing that we found in that forum, because that's the only mention of velocity at ever. So they probably had access to that, but it's not in the documentation. So yeah, that's what we're saying. We cannot trust that the training of these models has seen the complete documentation for LAMMPS. So the other thing that we are doing in this work is we created a parser, which is a linter in reality to catch common syntax errors. So as we said, the LLMs are not experts in the domain specific languages. They're a little bit better because they can generate faster and they can go and explore. And some of that is in their training. So we created this parser to catch syntax errors by translating these domain-specific languages into more structured forms. So the example here would be, right now, if I want to do periodic boundaries, it's boundary, then PPP. There is no tool, as far as we know, that if I put PPX, which is not a correct command in boundary, that it would let me know before I run it that it's wrong. So that is in the documentation. I could easily go and find it, but it's not like I have like an extension on like an IDE that just underlines it red, like this is not a thing. That would save me time. So we created this parser in a way to, with the goal of faster development and easier debugging and overall a better user experience. We believe that this parser and linter would be like a great addition to the LAMMPS GUI, for example, that already has autocomplete and autocorrect and highlights the different commands. If we can add something like this where you have an extra check for each of the commands that the options and arguments that you're passing are correct, this is what we're trying to do with this parser. So we're still writing the paper on the parser, but we're going to use it today. You're going to be one of the first groups to demo the parser, but we have a lot of requests for feedback on the parser. We haven't added all of the commands on LAMMPS. I think we added the 50 most popular ones, but because LAMMPS is always evolving, there's always more options. So it's still a little bit limited. And we encourage people to contribute if they desire. This is an open source project that we're kind of head starting. But yeah, so the other thing that we're going to do so that we can use these LLMs is we're going to have a parser so that you can run the parser before you run the actual simulation. And it can catch some of the basic errors that the LLMs do that we assume the humans might also do. We created this parser using a package called LARC, which is widely used for Python linters. So in Python, if you ever coded in Python, if you misspell the word print for one of your prints, it's going to tell you that it doesn't exist immediately. It's kind of like that. So we based our intentions and like we based our inspiration was one of these packages. So the current parser status is that it has the 50 most common commands as we found. So this is the 50 most common commands that we saw the LLMs use. And it's for the August 2024 version. So we're already one version behind. I don't think that many of the commands change, but we still have to work a little bit on getting the parser to work. So the schematic that Ethan was showing you yesterday in his presentation was kind of like our dream of what autonomous workflows might look like, where the only thing that you have to really put some scientific thought is how do you ask for the simulation that you want with the most amount of detail so that the rest of the steps work as flawlessly as you can make them. So the exercise that we're going to do today is going to follow something similar where you're going to write a prompt. It's going to generate a script. We are going to use NanoHub. We're from Purdue, so I'm going to introduce what NanoHub is, which is a platform cyber infrastructure where you can actually going to be able to use HPC resources at Purdue to run your calculations. And then we're going to do some of the output analysis as well. So if you were here for Ethan's presentation, this is like the little video that Ethan showed you where you can go all the way from the English description to the plots that you want with a few buttons in the middle. So the way that we're evaluating LLMs and the generated scripts is through these 4 steps. The first one is a sanitizer, which I haven't talked about a bunch here. The sanitizer, what it does is it replaces variables so that we make the scripts easier to parse. So you can declare all of your variables, and the sanitizer is just going to put the numbers where they need to go so that the parser can recognize if they are valid values. Then the parser I've talked about, the execution is going to be at Purdue in the Gilbreth supercomputer at Purdue. And then the accuracy checker is where we're going to have you guys volunteer on telling us, did the LLM create the script for the simulation that you wanted? Because you know what simulation you wanted, you know what you're expecting. Did it do it right? So the most common errors that we found in our studies were that it's kind of common for it to miss pair styles and pair coefficients. So EAM versus EAM alloy versus EAM Finney Sinclair. The LLMs don't really know that those 3 are different. So sometimes they use an EAM alloy pair coefficient with an EAM pair style, and LAMMPS doesn't like that. So that's one of the most common errors that we found. The other one is based on region specifications. If you want to have 2 different bodies with a gap in the middle, the gap might be in the wrong units. The regions might be overlapping each other. So those are some of the most common errors. And also units, always important to keep track of units. Okay, so NanoHub. NanoHub is an engineering gateway that was created a couple of decades ago and has been funded by the National Science Foundation that aims to accelerate scientific discovery through simulation, education, and AI-powered tools, all in the cloud. So I'm not going to ask you to install anything. Everything is going to run through a browser, and it's going to run in HPC resources. It's accessible, it's free. Anybody can use it. Anybody can contribute. We have a lot of resources. Here you can see 8,000 resources, as in teaching materials, lecture notes, homeworks. Professors sometimes put their whole classes there for free. You can watch recordings, you can watch videos. We have 866, that might be a little bit outdated, published tools, that is workflows that people have contributed to run any sort of nanotechnology and computational material science workflows. And we've been cited a bunch of times. So for the activity that we're gonna do, you're gonna need a NanoHub account if you're gonna follow what we do. And Ethan is gonna give you a little bit more instructions on what the instructions for the activity are gonna be. So I'm gonna hand it over to Ethan.
Yeah, so first I'll just ask by a show of hands, how many of you have already registered for a NanoHub account? We put that in the on the description. Okay. There's a decent amount. But so you can just go to nanohub.org/register if you still need to do that and you want to follow along. So the tool as we've made it uses OpenAI API keys. But to make an OpenAI API key account, you have to spend at least a minimum of $5. And so we didn't think that necessarily everybody would want to do that. But if you do have one already, it'll be easy to plug that in the workflow. But so we've added a bypass version, so you can use your favorite LLM if you have one, or the free version of ChatGPT if you just go to chatgpt.com. And generate a LAMMP script. Or if you just want to bring your own LAMMP script and try out the parser, you can do that too. So today's exercise. So this is the sim tool that we're going to be running, the workflow that we're going to work through. You can use the QR code or the link here. You will need a NanoHub account to do this, but once you have one, go ahead and click that Launch Tool button. So I'm going to leave this up here for a few minutes, and we will take questions on the presentation so far, and then also if anybody is having issues with getting this set up. And then I think in a couple minutes, we will start talking about running through the actual workflow.
Yeah, so you can go ahead and open the link. Like Ethan said, we're gonna be walking around here if people need help setting up the NanoHub account or using the tool. The way that the exercise is going to work is that we're going to make sure that anybody that wants to run the exercise can run the exercise. Then Ethan is going to run an example here in front of everybody so that people can see it if they don't want to do it. And I'm going to be walking around helping people that are doing the exercise. So yeah. If you have any questions about the presentation, now would be a good time if you're not doing the exercise. Thank you, thank you.
Has anybody gotten it launched yet?
Yeah, the website NanoHub is also part of the single authentication login. So if you have educational credentials, you can use that, and that simplifies your logging and registering process by quite a bit. Did I mention that? Yeah, you mentioned that. So also, I'm going to mention that on Slack, Axel mentioned that the commercial LLMs do scan the LAMMPS documentation, that they see it in the logs. And then LLMs contain fragments of data from the mailing list and the tutorials. They also confuse internal variable names with keywords. There is a try command that you can use as well to do some similar checking. All right, how about now? Has anybody been able to launch the tool? 5 people? 6 people. Okay, we're gonna wait a couple more minutes because I see people typing in their computers, hopefully typing in NanoHub. But yeah, so like Ethan said, Axel said that we have confirmation that they are scanning the documentation. The new versions of ChatGPT also already come pre-installed with the search tool. So it can go, if you ask, go search online for something, it's gonna go and search it. So that might be some of the logs that the developers are seeing for LAMMPS. But I also would not be surprised if they did it beforehand for their original models, just scrape anything that they could get their hands on. All right, so I'm gonna pass it over to Ethan so that he can swap from the slides to the tool. And I'm gonna be walking around the in-person part of this, helping people. If people online are also running the exercise, I'm gonna be checking in case there's questions. But yeah, so we're gonna start the live demo of the exercise, and feel free to follow along. But just remember that it's your prompt. You can ask for whatever simulation you want. We're interested in knowing how good the LLMs are. So we might ask you for a few, like a bit of feedback after you use the tool for a little bit. Yeah. Okay. So I'm gonna get switched over. Yeah. Okay. All right. So I have already launched the tool, and it should look a lot like this. And so we have a bit of information at the top that you're welcome to read. But for now, I can just show you what's going on. So I was running it earlier, so I'm going to go ahead and actually click this clear and start new run button. And okay, so I have set my my alias to Ethan 2025. You can set yours to whatever you want, but this will be like a queryable identifier if to grab your data later on if you would like from the second part of the tool. So I will do a live example. And so then we have, I have an API key already loaded in, and it's not quite the whole API key, so you shouldn't be able to use it. But it does expire shortly anyways. So we have a set of example prompts. So these are the ones that we're doing in our paper and that the Sankey diagram is based off of. And so they're various levels of complexity. This one is just doing a simple equilibration. So this from here, I can just generate the script directly with the API key here. So it's generating the script in the box. Hopefully, yeah. Is this better? Yeah, okay. All right. So yes, so I have a script now, but I need a potential to run this. And so one of the things right away that I noticed is that the pair style is set to EAM and the potential I have is an EAM alloy potential. So I'm going to change that there. And then the name of the potential that I have, and this one is available. There's a link in the information at the top of the page to the potential to download it if you don't already have one or whatever you're going to run. So I've set this there, and then I will upload the potential. Okay, and then I have this sanitize/parse button. So I've ran through it. It says script parsed successfully, and then it gives me a breakdown of each individual command and then the things after it. So the command was units, the option is metal, and so on and so forth. So it has gone through the entire script and it doesn't see any issues. And so this is a successful sanitize and parse. So now that I have my script, I'm going to go ahead and click run. So this is going to send the job over to our cluster at Purdue on Gilbreth. And so you'll see the sim tool is now executing, and it'll give me a couple little information blips along the way. And so one thing that I did that you all should not do if you are running this example is run it for 500,000 steps. So if you cut it down a little more, your simulation will be done faster. And since we only have 20 minutes, the quicker the simulation, the better. Yeah. Other thing to take into account, I don't know how many people here work with HPC, but your job got sent to a queue. It might take a couple of minutes to start. Yeah. Okay. So the sim tool is running and this will take a couple minutes. So I'm going to go ahead and go back to the presentation. So what we want to do is a live examination of like how this works. So if you saw my presentation yesterday and you saw the Sankey diagram, which I can show here, we want to try to make a Sankey diagram live a little bit more simple than this one, where we have the script creation, the parser step, and then the simulation execution steps as like offshoots for the flow chart. So the Sankey diagram is here. Let me check on the progress of this. Yeah.
Yeah, to create this live Sankey diagram, if you go in, we're gonna show in the presentation here.
If you go to that QR code, it's like a little poll where you can tell us it worked the first time, it crashed in the parser, it crashed in the execution, just so that we know how good the scripts that you guys are generating are, and we can use it for our purposes of knowing what the most common things are. So Ethan is going to create this Anki diagram very fast with the responses of this poll. Hopefully, we can get some responses in the 20 minutes that we have left. But yeah, so if you go here, you can find that. For now, we should focus on getting people running the tool. So if anybody here in person has any difficulties, just raise your hand.
But it isn't going to have my caption. That was trying to. Yes, you can click the bypass, we just don't do it. And then you just put it there, okay, we just say it again. Okay, so you put that in. I feel like I tried it. I mean, of course, I mean, with your runs make it work. That's how it's going to work. Yeah, it's not. And you click bypass. Oh, I see. Okay, I see. You're not actually. So the bypass is so that these two days would translate like but from here on the concept. I think that was my question. You go to the example of that. But if you replace it with your script and then you get the bypass. That and then you go venue parts and okay. Yes, so it's a compilation of labs. Anything that you can run in labs, all the plans on board, you can run. You do this the polymer system. So the only thing that it does is it takes your lab script, your input script, your potential script, and then you combine with the selection with an potential input with the concentration. Yeah, we added another concept to it. Yeah, this is an educational version. We added another topic of the structure. So if you want to get the structure of the whole unit, so you can add that too. You can add that. So I'm pushing the expecting to this system. We can use the that would be that division. Which yeah. So that is that. Yeah. This one is just we have really good pick. Yeah, so it's very easy to
Okay, so how's everybody doing so far? Is anybody else having any issues? Are people getting it to run? Yeah.
Yeah, this is figured out. Oh, so these were the special. Okay, so you could be like, I want to put on the simulation. The bypass here, it's going up. So this is English, or you be the line? I'm just trying to say, do it like this, like. Oh, then, so, to go from here to continue with the paper, so. Oh, or this then allows you to use the API. So you can only use like English. Yes. So you will use English and then the API.
Okay, so we have a question from the in-person audience that I think would be good to explain. So if you are not like me and are not using an API key, so the setup process is slightly different, and you still need to fill out this run or this alias box, and you need to fill out this run identifier. But then once you have that, you'll need to click this bypass key so that you don't have to do these boxes to activate the LAMP script box. So, and then once you have this box where you should put your LAMP script, whether from your favorite LLM or from the free version of ChatGPT, you'll need to click the edit button. And then you can copy and paste your script or write your script in here. And then you can use the sanitize parse button. And then run or add your potential structure file if you have one. Okay, and then also, so mine just finished. So I'm going to show you, we have a few different ways to download it. So you could download a zip if you are outputting dump files and need those for some sort of analysis. But for now, I'll just download the log file so that I can take a look at the run. So you'll see that I have my results for my 500,000 steps, and they are automatically loaded into the system. So I'm going to query for the runs info, hopefully. Let me see. Well, the querying is not working. Is it? Has it not? Where? Yeah, I just downloaded the log file. Maybe just start with the. Yeah, I can do it. Okay, so I don't know why the querying isn't working for this, but I do have, or I have ran this tool many times before, so I will query some past results that I have. Hopefully. So I wonder if we're having an issue on the back end, because this makes a call to our database there. Okay, well, so that's not working for the moment, but I will show you the other features where we can, again, call the API to generate a method section. So this is then explaining what it thinks is going on. And for the most part, we've seen that these are pretty well descriptive, right? So explaining the lattice structure, explaining what exactly we're using. It says embedded atom model, says the potential, and gives like a little bit of extra information as well. But again, this is not necessarily perfect description. But it seems to describe the input scripts fairly well. So so mine went all the way through, right? I sanitized and parsed, that was successful. I clicked the run button, that was successful. And I haven't got the querying part down, but for this interactive example at least, we have the results. So I'm going to go ahead and put in my results by scanning the QR code. So let me start the interaction. Okay, so mine, out of these 4 options, it parsed and it ran. And then let's look at the accuracy really quick. So, okay, so I ask it for an NPT ensemble for 500 picoseconds, 300 Kelvin, 1 atmosphere, Nosy Hoover thermostat. So we'll go through. So we have FCC. We do have an FCC unit cell 5 times in each direction. And then the pair style was embedded atom model instead of EAM/alloy, but we didn't specify that explicitly. 5 by 5? Oh, it's a comment. Sorry. Yeah. And then so we're using aluminum, that's correct. We're using the NPT ensemble at 300 Kelvin, 1 atmosphere. And then so we mentioned the relaxation timescales of 0.1 and 1 picosecond, but I think, yeah. Okay, so then the final, we have the 500 picoseconds or 500,000 steps times 0.001. And I think that that's the correct math. Okay, so I will say for mine that it parsed and it ran and it seemed accurate. But of course, this isn't necessarily a super complicated LAMP simulation. And one that we've tried several different times to run. So I will check this periodically if anybody else's results come in, and then I'll ask again what everybody in the audience's progress is. Okay, so I'm going to go back to here, go back to here. Okay, is there anybody else in the audience needs help? LAMMPS results for using. Oh, okay. So this is like the dump file. Yeah, this is the dump file as YAML format, and you can also download the log file, which is the standard output for LAMMPS. So you need to do that for something. But let's complete it. Oh, okay. So it's gonna interpret it. Yeah. All right, so we are getting closer to when the breakout room finishes. So we're gonna kind of give a few final conclusions about our work. So we got some participation here from the in-person audience. And if you have time, go to this QR code so that you can help us create this live Sankey diagram of whether or not the scripts worked. So in our experience, this is similar to what Ethan presented yesterday. We found that about 35 of 120 worked, which is like a 20% accuracy of it worked from beginning to end. It did everything correct. All the other ones were failures. So we can all be safe for now that we're not going to lose our jobs because this is really bad at doing LAMMPS, at least the commercial version. But the models are getting better every day. This, as you can see, is already not including GPT-5 that came out this week, last week. So new models are coming out. But in our experience, it still has a lot of errors that need to be caught. As a conclusion, LLMs are ready for this application space and are useful as in they can give you a good head start on what the script is going to end up looking like, but it still requires a little bit of debugging. And we want to emphasize that these tools are going to be collaborators and co-pilots in our journey to creating simulations. They should never replace people. You should never just trust that the LLM is going to do everything correctly. You should still verify it because if you let the LLM do everything, then when you go to the part where you're interpreting the results, you might not know what happened. So it's always good that the human is in every single step. And because of the hallucination problem that LLMs have, not everything that the LLM generates is true. It might be very confident, but it might not be true. And as a conclusion about the parser, we're going to take some of the advice that we got from Axel during the presentation, but we are still working on the parser. So if you're interested in contributing to our parser, here's a QR code where we are looking for people to basically help us expand the version of the parser that we have right now. So our parser is dependent on a grammar that basically takes all of the LAMMPS documentation and decides which arguments are correct or not. So we're still building that grammar. So with that, we're going to finish the breakout room. We're going to be here for the rest of the day if you guys want to keep trying. And we appreciate people trying the tool, and we're open for questions. Thank you.
Okay, we're not on a super rigid schedule. We'll take time for a couple questions if people have them. So I want to make one comment. I know you're measuring accuracy, your 20% or whatever is it. The script ran, everything was correct, it was perfect. But it seems like it could still be a big time saver for people if the chat GPT got it 90% right, and you could look through and you'd see a couple errors, or you just have to change a couple things. I mean, it seems like maybe your metric for success is too high.
Yeah, the
I don't
metric
know.
for success that we wanted was basically the movie Iron Man, where Iron Man is talking to Jarvis and Jarvis does everything. That would be 100% success. We understand that we're not there yet, but yeah, so we agree that just getting the LLM to output something that looks like a logical LAMMPS simulation, like the simulation setup is correct and the ensemble is correct and there's just a few details, that's still kind of a success. And maybe we should consider it more as a half success of our accuracy.
Yeah, I know when I write a script the first time, I'm not 100% correct. And so the process of, oh, what went wrong? Where did it go wrong? Looking at your script, that's something I think any user has to do. And if this saved you some time in that process by getting you close, I don't know. Does anybody else agree with that? All right. Well, let's thank the speakers again and for the nice breakout. You want to do that? Okay. So Richard's going to tell you about the three-way split that's coming up next. And I'll just say when the next hour is over and you come back, I think we have a break on the schedule. Is that right? So there's a break. You can meet in the lobby and then we'll come back in here for for the last developer section, and Stan will give some remarks, and we'll just have a group discussion about ideas for LAMPS if you want to contribute to that.
Okay, so we're going to split up into 3 groups now. There's breakouts track B, C, and D. And so the Aaliyah with breakout B is going to be in this room, so you don't have to move. If you want to go to the NIST breakout, that's going to be track C in the room B. That's right behind the lunch room in the back. So if you go out, go right. There's a hallway next to the lunchroom. Go all the way to the back. There's this lecture room. And then Peter's is going to do a breakout about EMC. If you go out here to the right, opposite to the lunchroom on the left, there's room D. Okay, and as Steve said, afterwards we'll have a short 15 minutes coffee break again. Do you want the body shape? Yeah, sure. We can wander around.
Make sure this one's turned on. Check, check. All right, excellent. Is everyone ready and excited for this? Let's see. I intended to share my entire screen, so let's see what I'm actually doing.
The atmosphere with the other, there's a mismatch between the resolution that it just cuts it off. But it only happens when you're doing a video Zoom sharing. I don't know. So yeah, it's like it's zoomed into a proportion.
Yeah, and that's not something that's on your side?
Yeah, it's only on the, no, actually it's also on the live stream.
Yeah. It's not going to help. So yeah, my entire screen's cut off. Let me try something. Oops. I wonder if I just maybe change my resolution to like 16 by 9 instead of 16 by 10. I don't know if it'll let me.
Okay. Looks at least better. Yep.
Oh, excellent. All right.
Perfect. Yeah.
Strange hack. All right. We are good to go now. So welcome to this breakout. Thank you all for coming. I will talk about more in detail what I talked about. So because that hand is from that computer.
Didn't touch it.
Is there like a misbehaving touchscreen going on or something? Because that is what's happening.
Okay.
Yeah. Yeah. Hopefully. Okay.
Yeah.
Do I have the permission to touch that computer if something else happens? Okay. Thank you. All right. So hopefully we're done with the technical issues. Yeah, I will talk more in detail what I talked about in the last in my 15-minute talk. Specifically, crystal genome, which is our effort to generalize OpenKIM material property evaluations to generic crystals. So here's the plan for the breakout session. I will first talk about crystallography and the A-flow prototype label. And I'm going to get my phone so I have a clock because I can't see the time. But yeah, so I'm going to spend actually quite a bit of time talking about crystallography. Which is very important for understanding how we organize crystals, and I think it's very important for material scientists in general. Then I will give a more in-depth tour of the OpenKIM website than I was able to during the 15-minute talk. And then finally, I will demo using the KIMBV package to run OpenKIM calculations locally. And that'll be a pretty short part, maybe like 15 minutes, but you will be able to follow along with a public binder. Okay, so starting with the crystallography section. So to reiterate, crystal genome generalizes the OpenKIM framework for evaluating material properties to arbitrary crystals. We already have 32,000 materials, and we have a straightforward path to add millions of materials. So we need a way to organize all these materials. Some ways to organize materials are just naming them, like diamond. So on the left here, you have a little crop of a part of our website where we have a diamond crystal, and we have this crystallographic description of it. So you can name it diamond. There are Strukturbericht designations. Hopefully I didn't butcher that German too much, such as A4. That's what the structure for diamond. These are unfortunately incomplete and non-generalizable. If someone invents a new superconductor tomorrow, it's not going to have a name, unless they give it one. And same with the Strukturbericht, that there's some methodology to what the letter means, but there really isn't. It's still just arbitrarily putting things in those bins, and eventually you start putting subscripts and primes and stuff like that. Another way to describe, to classify materials is just to give them a number. For example, in materials project or in OQMD, they just say, the ID for diamond is MP149 and OQMD 5714. That is not a descriptive way to describe crystals, because that doesn't tell you anything about the crystals. And then finally, you can just give the coordinates file, but that's very cumbersome, and that's not a unique way to describe the crystal. And even though I've talked badly about all these different ways to describe crystals, if you want those descriptions, we do provide them where they're available. On the left, you can see that we say that it's diamond A4, and you can download the coordinate file. But the solution, we believe, to describing crystals in a very general way that is descriptive and unique, with an asterisk that I'll talk about later, and automatically generalizable is crystallography, specifically the A-flow prototype label, which is this thing you see here. So that is the A-flow prototype label for diamond. And it looks probably very complicated, but I'll spend the next 10 or 20 minutes hopefully elucidating that a little bit. And another thing about crystallography is that crystallography relates to material properties. And for example, the crystallographic group of a material restricts what form the elastic constants of that material might have. So I think it's just very important for material scientists, like I said, in general, and I'm saying that in this slide too, that when I say crystallography, I mean the international tables. That's the de facto standard for organizing all this info. And if you study bulk crystalline solids, I think you should read it because I can't teach you about it in 10 minutes, and it's a very good source of information. Okay, so jumping right into it. I won't get into super formal group theory, but I'll just give some simple 2D examples to hopefully help you understand these things. So the Euclidean symmetry group of an object is the collection of all rigid body motions, including improper motions, so things that have a determinant of -1, that leave the object invariant. For example, the Euclidean symmetry group of a rectangle includes doing nothing. If you do nothing to an object, you don't change it. Mirroring about the x-axis, mirroring about the y-axis, and doing a 180-degree rotation around the center. A space group is the symmetry group of a theoretical crystal filling the entire universe. That might sound a little strange, but that's actually what we are assuming when we do periodic boundary conditions. And I will be using 2D crystals filling in 2D universe for examples, just for simplicity. And these are technically characterized with plane or wallpaper groups. Okay, so like I said, we're combining, to make a space group, or in this case, a plane group, we combine those rotational symmetries of the rectangle with tiling the infinite plane with this rectangle. And this is plane group number 6 with the symbol P2MM. Another great resource for crystallography is this Bilbao crystallographic server page, where you can get these great tables, and actually a lot of the software we developed at OpenKim for crystallography is just built on parsing these tables and importing them into Python and doing calculations on them. So we're going to build a 2D crystal by adding atoms to this lattice, and we're going to put them at Wyckoff positions, and hopefully you'll understand what a Wyckoff position is just by example. So position A in this table is the corner of the unit cell. You can see this coordinate is 0, 0, so that's pretty clear. You just put 1 atom at the corner. There's 4 on the picture, but that's because they're periodic images. There's 1 A atom per unit cell. Then position E, if we move up this table, that has a so-called multiplicity of 2, means it has 2 coordinates. Because if we only put a 1 atom in this position and not at this position, then we would break the symmetry of this plane group. It would no longer obey the rotations and mirrors. However, because E has a free parameter, this X, we can actually put multiple atoms at that position. So there can be multiple instances of this Wyckoff position. And then finally, every group has a general position. So the positions we looked at before, they coincide with some symmetry element. They're on a mirror plane, or they're on a rotation point, or both. The general position, because it doesn't coincide with any special symmetry, it must be replicated by every symmetry operation of the group. So that's this I letter for this case. And in fact, the general position is an expression of all the rotational operations in the group. That's why the rectangle has 4 operationals, and the general position of the rectangle corresponds to 4 coordinates. And combining this general position with the so-called crystal family that can be roughly thought as the shape of the cell is what uniquely defines the plane or space group. And mathematics allows for only a finite number of such combinations. There are only 17 types of plane groups in 2 dimensions, and there are only 230 types of space groups in 3 dimensions. So now we can build for this fictitious 2D crystal we've built, we can build a 2D analog of the A-flow prototype label. And here I'm indicating different atom types with the different colors. So the first atom type is maroon and the second atom type is gold. So we start with the group number 6. As I said, there's a finite number of these and they're numbered in a conventional way in the international tables. Then we separate these things by underscores and we put a section indicating what positions the maroon atoms are at. So that's A and I. So that's the Wyckoff section for the maroon atoms. And then we do a section for the gold atoms. And because there are 2 instances of the E position, we put a 2 there. So that's 2E. And this is actually a full description of the symmetries of the crystal. There are a couple more sections that are redundant just for information. There's this Pearson symbol. I put it in quotes because I don't know if it's actually formally talked about that way for 2 dimensions. I just kind of created an analog. And that tells you what lattice it is. So this is a rectangular lattice that's primitive, which means there's no subtranslation. So for example, like F face-centered cubic, the centering would be reflected in the Pearson symbol for that. And then 9 means there are 9 atoms in the unit cell. And it's redundant because we can infer what lattice it is from the group number, and we can infer how many atoms there are in the unit cell by counting the letters in that table and their multiplicity and stuff like that. And same thing with the stoichiometry that's also provided just for convenience. You would add together the different Wyckoff sections and then divide by the greatest common divisor to get the stoichiometry. So those are the discrete kind of variables describing the crystal. There's also the free parameters allowed by the lattice and by the internal free parameters. So in addition to the prototype label, we have to specify, in this case, the A lattice parameter, the B lattice parameter, or the B over A ratio. And then we have to specify the X coordinate for the first E position, the X coordinate for the second E position, and both X and Y coordinates for the I position. And that gives a full symmetry-reduced description of the crystal with just 6 free parameters. And compare that to if we were to give the full lengths and angles of the cell and the individual coordinates of each atom, that would be 21 free parameters. And of course, for more complex 3D crystals, this difference can get much more dramatic. So here are some here's a figure from the A-Flow paper. This is the A-Flow library part 4. That's the paper I would read for a formal definition of the prototype label. This here you can see the commands that you would use in the A-Flow software to generate crystals. And so this is the meaning of the little asterisk I put at the beginning. So these 2 crystals, they're visually obviously quite different, but they have the same prototype label because they have the same symmetries. They have the same space group and they have the same occupied Wyckoff position, just one in this case, F. But they look quite different because their free parameters are quite different. So because of this, we can't completely avoid arbitrary labels. So if this happens, we have to, label one as A and one as B or something like that. But this is very rare. Once you specify the prototype label and the species, this happens to less than 5% of crystals. And of course, I should mention that this is kind of this use of crystallography to just describe and classify crystals. It's the study of crystallography also goes the other way, which is given a crystal, characterizing it, saying what symmetries it has. And experimentalists do this, of course, with X-rays and stuff like that. And there's also the computational part of it where you give me a coordinate file and I analyze it and tell you its symmetries. And that's done with various software like the AFlow software and software that we've written in OpenChem. So I'm almost done. I just wanted to show this one really confusing part that I think that really confused me and might confuse you when you're looking at symmetry reduced descriptions of crystals. So on the left here, I have pyrite. It's a cubic crystal that has space group 205. Cubic crystals are in space groups between 195 and 230. Has two free parameters, one internal free parameter and the box side. On the right here, I promise you these are different crystals. I can't promise you that they're in the right spot on the slide. This crystal also has cubic lattice vectors, but its internal positions break all rotational symmetry. So this is actually space group 1. It doesn't have any rotational symmetry, and in order to describe it, you do have to specify every single length and angle of the cell and every single internal coordinate. It just so happens, incidentally, that the lengths and angles of the cell correspond to a cube. So that's the crystallography part finished. Now I'm going to give an in-depth tour of the new OpenChem website, and I would encourage you to follow along. We might crash the website. That's okay. I have backup slides, but I was told by our webmaster that there's a lot of queries involved, and it might crash the website. Okay, so let me get my notes out. Okay, so there's this our brand new web page, and here this is the bar to type in elements that you're interested in. You can either search for potentials for that element, which is I won't focus on that today, or you can search for predictions, which is the part I will focus on now. If you just search for whatever you're interested in, I do encourage you to do that, but it's likely that you'll see some missing results. This is because we are simply churning through the computations. All of our computations are done automatically, but they're waiting in queues on various HPCs around the country. You know, we're trying to do, I don't even know, probably hundreds of thousands of computations. They're all not very long, but they're just waiting in queues. So I'm going to search for something that I know works, specifically silicon, to start with something simple. And that takes you to this search by compound page. And there is these various drop-downs to filter your results. Right now, below you'll get a table for all results that we have for silicon. There are all these various question marks that tell you what the different selections mean. And there are different question marks here that tell you what the columns mean. And so here, for example, I'm going to focus here on diamond. You get various information about it, like its human readable name if it has one, crystallographic information like the space group, its AFlow prototype label that we discussed, and various summaries of what we've computed for it. So the total number of computations we've done for it, how many unique properties those computations spread over, and the number of models that we've computed with this crystal. So now I am going to go right here. And this loads this page for browsing predictions for this specific crystal. At the top of every one of these pages, there's this automatically generated crystallography panel that you already saw a screenshot of. So this is a short explanation of the things that I talked about in my presentation regarding crystallography. It kind of parses out the meaning of every single part of this A-flow prototype label. Okay, so now I'm going to select a potential. I'm going to select the classic Sillinger-Weber potential for silicon. Silicon is obviously a very well-studied material, so it has tons of different potentials. There's a link here to the page for this interatomic potential. I'm going to click here really quick. Again, I'm not focusing on this part of this aspect of OpenChem for this talk, but this is where you would learn about the potential. And when if you click on this, this is what takes you to kind of the guide of how to get yourself set up running OpenChem potentials in your simulations. Okay, so then going back to here, I will talk about why this. I guess I already talked about how a single prototype label might have different structures corresponding to it. This just has one structure because it has no degrees of freedom. It's just cubic diamond. So I'm going to open this section. You can see it's slowing down a little bit already. So let's see. Okay. Yeah, so there's this visualization of the structure. You can play with it, rotate it. We have a lot of really cool buttons here. You can get a bigger view of it. You can look at it with different orientations. Maybe I'll play with it a little bit more when I show a little bit more complex crystal. Then, very importantly, you can just download the Pascal file for this crystal, and that is the relaxed configuration for this specific potential. So this file you download is different for every potential you choose. Okay, so then now below this, you have all the properties we've computed for this crystal. And I am going to choose the elastic constants. As I've mentioned already, we are very focused on crystallography. So, for example, these elastic constants, because the crystallography of the space group of a crystal restricts what is the form of its elastic constants matrix, or what unique elastic constants it has. Here we report a table of the unique elastic constants. If you know that cubic crystals only have 3 unique elastic constants. We show this picture of the structure of the elasticity matrix. And I guess just back up a little bit. When possible, we try to compute uncertainty as well. So here we report the uncertainty for these computations. Because this is a very well-behaved potential, the uncertainty is very low. Then all of these different fields have a blue question mark, which if you click on it, so this, for example, this elasticity matrix structure, it's kind of meaningless without an explanation. So if I click on this question mark, that tells you kind of what the small dots, the connecting lines, and stuff like that mean in that picture. And then below we show the full elasticity matrix. And I wanted to. We have this really cool thing. You might have seen this in Materials Project. This is a third-party website by Francois Codea. Who very graciously provided us with an endpoint, and you can visualize all kinds of cool things about these elastic constants. First of all, you can get the various averaging schemes if you know what that means, or you can get 3D views of the Young's modulus and shear modulus and Poisson's ratio for this crystal. Very cool. So if you visualize in 3D. Okay, it's not working. That's why it's not working. That's why the thing wasn't loading, is because apparently my browser is currently misbehaving and WebGL is not supported. But if you'll see kind of a 3D shape you can spin, and you can see that, diamond is more stiff along the diagonal and stuff like that. Okay. Then on the right side, we have this bar chart of all the different potentials comparing their predictions. Right now, we don't have reference data for elastic constants. I'm in the process of adding DFT reference data to compare to. And you can choose up here which elastic constants you want to plot, C11, C12, and let's go back to C11. And then you hover over these potentials and you can get information about their prediction compared to the mean and standard deviation. Down here, if you hover over these potentials that are way out of the way, you can you will be able to see that most of them are for silicon compounds, which is why they're not good at describing elemental silicon. And then finally, if you click on one of these bars, you get a short description of the potential, which is essentially usually a paraphrased abstract of the original paper. And if you can once again go to the page for the potential where you can get much more detailed information about it. And another thing I want to say is that I'm kind of telling you how to access this information through the GUI, but all of this information is available in our publicly facing MongoDB that you can query. I just don't think there's much point in demonstrating querying. If you need it for your application, then please contact us and we'll talk to you how to get to our database. I guess I can just show that there's a button up here for querying the repository, and then you get your interface for directly tapping into the MongoDB. And related to that, at the bottom of every one of these panels summarizing this property, you can also click on link to test result, which will give you the raw data that is displayed there, all the files and stuff like that. Okay, so let's do something more interesting than diamond silicon. I'm going to click reset species here and go to iron carbon and search for that. So I'm going to use this short name dropdown, which contains all the human readable names. And specifically, there's a specific thing about how that relates to symmetry. So the specific short name corresponds not only to the symmetry of the crystal, but also the free parameters of the crystal. So a really simple example that's explained here under this question mark is that people will often colloquially say HCP for a crystal that is not actually close packed. It's the crystal that has the HCP hexagonal close packed planes, but the C over A ratio isn't actually close packed. And we think that generally when people search for HCP, they'll want to see all results of that symmetry. So when you pick a short name, here I'm going to pick this B2PD5 structure. Even though this is called B2PD5, that's just the compound that the structure was named after. Carbon iron also crystallizes in that structure. When I pick this, I'm going to get not only this exact structure, I'm also going to get all the structures with the same symmetry. So this is a pretty fine point, but we've tried to explain it both here and here. This is why there are multiple rows as opposed to just one row for the diamond, is because some potentials minimize their free parameters to the actual structure of B2PD5. And then some of them, there's also this other structure that has the same symmetry. None of the potentials for carbon iron relax to those free parameters. And then we have this top row that's a catch-all for all structures that don't match any known or any recorded crystal that's in the AFlow database. But we still detect and report its symmetry, the prototype label, because again, the prototype label is fully general. It is generalizable to any arbitrary crystal. It is a description. It is just a mathematical construct that describes the crystal. And like I said, we've tried to explain it in these help boxes, both under short name and under prototype. So I'm going to explore the results for this monoclinic iron carbon structure. And let's see what I have in my notes. Right, so I'm going to pick a specific potential. I'm going to pick this ASLAM potential to show that in this case, this potential relaxes to two different sets of free parameters. So if I open these, so I have to go to the annotated view that doesn't use WebGL because my browser is misbehaving. So maybe I'll zoom way out. So you can compare, whoops. Yeah, you can see that these, even though they have the same symmetry and the same occupied Wyckoff positions, they have different, they look different, similar to that picture I showed from the A-flow paper. Okay, so let me zoom back in. And I'm going to pick a different potential. I'm going to pick this Kim Jung and Lee potential. I think it's this one. Yeah. Yep. So if you will notice that each individual structure has its own crystallography panel. And here we indicate that this specific potential, so the crystallographic information at the top of the page is the general crystallographic information without relating to any specific set of free parameters. So there's never going to be a short name here. Whereas this specific potential has, because we're dealing with its relaxed structure, it has relaxed to the specific free parameters corresponding to this B2, PD5 structure. And that's reflected in this crystallography panel. And here as well. Okay, so then we're going to look at a different property. I think this one's very cool. I mentioned it during my 15-minute talk. Not this one. The energy and crystal structure as a function of hydrostatic pressure. So this is where we scan over pressures and we relax the structure under stress boundary conditions at each point and give various graphs of it. I think this is a pretty simple computation, but I very rarely see it. Usually, even with anisotropic crystals, people just expand and contract isotropically, which is a pretty meaningless way to look at a structure, because when you apply hydrostatic pressure to an anisotropic crystal, it will behave anisotropically. So for example, if we scroll all the way down, we will see that the B/A ratio changes as you compress the crystal. Same with the C/A ratio and the beta angle. These are a combination of a linear and log plot, because crystals, a lot of the interesting stuff that people are interested in will just happen around zero pressure, but you can compress most interatomic potentials to a really, really high pressure. And there are some applications like, the Earth's core or shock applications where you are interested in high pressure. So we've chosen to plot them on these combination linear and log plots. And same with the energy here. Here, actually, the combination of linear and log is on both the x-axis and the y-axis. So the x-axis is the pressure and the y-axis is the energy. Okay. Okay, so then this concludes the demo of the website. Now I'm going to demonstrate the KimVV package, which allows you to perform these calculations locally using your own potentials. So we go back to the presentation. So for installations, this is the GitHub for the package. There's installation instructions there. It is installable from pip, but it does have some non-Python prerequisites that must be installed first, specifically the A-flow software. And that's all explained there in the README. So this package, as I said, it runs the same OpenKim computational protocols as we just saw locally. And test drivers is just the OpenKim parlance for these computational protocols. So you can run these with Kim models. This includes local models that haven't been updated to openkim.org, because if it's already on openkim.org, why would you run it? You would just look on the website and we already ran it for you. The documentation for the Kim API is here, and there you can read about how to create your own potentials locally. What this means practically is that any LAMMPS pair style and set of parameters can be made into a local Kim model and ran with these computations. You can also run it with any ASC calculator. So I've used this package with DFTB. but it theoretically should even work with DFT. Okay, so then if you would like to follow along for these last 20 minutes, then if you prepared ahead of time on the workshop website, you would have either done a local installation or you would have downloaded this Docker image. Otherwise, you can use this public binder. It's at github.com/openkim/openkimdemo. I'm going to give you a second to type that in. And you will need to scroll down to the README and launch the binder. So I'm going to give everyone a few seconds to do that. I'm going to ask a very specific question. Did anyone do a local installation ahead of time and you have an Apple Silicon Mac? Raise your hand if that is true about you. Okay, good. This is just a small detail about the Conda installation of on Silicon Macs of the Kim API. It doesn't come with example models. It works just like any other installation. It's perfectly functional. It just doesn't come with example models, and we're going to be using example models. Okay, so in order to not rely on this, I guess, does anyone need more time? Okay, I'm going to get going then. I'm going to launch a local version of this binder, so I'm not relying on the public binder service, but you should see something very similar to what you would see if you opened the binder in your web. Yeah. Mm-hmm. Oh, yeah, that's a great idea. Thank you. Oops. I guess. All right. Thank you. Okay, so let me just navigate real quick. One comment that I didn't mention is that this KimVV package isn't really, at least at this time, meant to handle workflow management or anything like that. If you want to do complex workflows, you would have to provide that yourself. Or you could use that Kim developer Docker image that I mentioned, because that provides an emulation of our pipeline. So that has all the dependency handling and stuff like that that the OpenKim processing pipeline has. Okay, so then this binder is actually a great demonstration of a lot of different aspects of OpenKim. We're only going to focus on one specific aspect, but if you just want to learn about OpenKim and explore what the OpenKim project can provide for you, I would encourage looking through this binder. But I'm going to specifically go to this the section called KimVV Python package and open this link right here. And now please raise your hand if you have any questions or if you're having issues. Okay, so then you should, this is just, these examples are just copy and pasted from the KimVV README. So you can just run those in Python as well if you have the Docker or if you have the package installed locally. So I'm going to go through a couple of examples corresponding to the two properties I showed. I'm going to show the elastic constants and the pressure versus crystal structure scan. So first, as usual, you would import all the different packages you need. So in KimVV, in the documentation, it's listed what computations are available, and they're just they're named like this. So for elastic constants, it's called elastic constants crystal. I don't know why that's happening. Okay. Okay, then the way you use these is first you instantiate the class with the model you want to use. And this model can be either a string indicating a Kim model name, or it can be a ASE calculator. So in this case, I'm going to use this example Leonard-Jones model that comes with most installations of the Kim API to instantiate my object. And then to perform the computation, we will call this object that we've instantiated. But first, we are going to read the documentation corresponding to this computation by using this print doc command. And that is going to print a description of the method and all the arguments of it. And then at the bottom, it'll give you the defaults. So if we were to read this in detail, you would see that in order to compute elastic constants in OpenKim, we do a robust computation loop where we actually try several different methods and choose the one with the lowest error, unless we have below error tolerance right away. And then we just say, okay, this is good enough. We check both error as far as, because this is done by numerical differentiation, we check the error of the numerical differentiation with Richardson extrapolation, if you know what that is. And we also check the deviation of the elasticity tensor from the material symmetry, because every material, every crystal material has a specific form of the tensor that it must obey. Let's say we've read this in detail and we decide that we actually don't want that computational loop. We want, for the sake of speed, we want to compute it using a faster method. I don't know why this is happening. Maybe if I close this. And yeah, so we're gonna make an atoms object, just bulk argon. And then we're gonna, like I said, to do the actual computation, you invoke the instance of the class that you instantiated. And the first argument is almost always going to be the crystal structure, which can be an atoms object, and then you pass any other arguments, which here we've decided that we want this stress condensed method to compute the elastic constants. And all dependencies are resolved automatically. In this case, the dependency is you want to relax the crystal first before computing the elastic constants. So that's what it's doing first. And it's reporting all these things. Do you have any questions while it's running? All right, so now let's move on to computing the elastic constants calculations. And it's very fast. So computing the elastic constants of argon is not very complicated, so it was fast. And the reason why it's having these pauses is, again, because we are very focused on crystallography and we are doing a lot of crystallography computations in between. So right now, what it's probably doing is checking the symmetry of that elastic constants tensor and actually propagating. So we also symmetrize the tensor and give you the symmetrized version of the tensor, and we properly propagate error through all of that here because it's, yep.
You run the calculation and William runs the calculation. Does it run the actual script again, or do you just retrieve the results of one of them?
So this, it actually runs the script because, so this model that we used at the top, this model is not in OpenKim. So it's running things locally. So this is intended for you to run with your own models. So, for example, you are very sensitive about your model, and before you upload it to OpenKim, you want to make sure that it'll give good results on the exact protocols that we use. This is what you would do to compute it locally. Thank you. Okay, so then, yeah, so then you get your elastic constants, and then it returns a dictionary. When we called the elastic constant computation, we assigned it to this results variable, and what that is a list of dictionaries. And I'll print it right now. It'll look pretty intimidating and have a lot of these confusing fields. And what that corresponds to is what we call a Kim property instance. And this is a long-standing way that OpenKim does things. So if you go to openkim.org/properties, that's linked there. This will actually take a while to load as well. I might not even wait for it because it's querying for all there is. Oh, there we go. Not that slow. So this is a list of all the properties we have. So at the top, you see the property ID. You see that this property is called elastic constants and isothermal MPT. And you can find that here. Not the cubic one. This one's restricted to cubic crystals. This is for general crystals. So you click on this, and this is actually the same page that the questions marks linked to. And this will give you a very rigorous definition of every single key in that dictionary and what it means. And we really try to make these very rigorous definitions of material properties. In fact, we try to make them so rigorous that you could actually report experimental data using these as well. Okay. So then we have about 10 minutes left. I'm going to show the second example. So very similarly, I'm going to import the crystal structure and energy versus pressure computation, which is that pressure scan. And again, you can see in the KimVV README, you can see all the different computations available. And instead of using a Kim model, I'm going to use an ASC calculator. I'm just using EMT here because it can be fast. And again, instantiate the class with the calculator or model you want to use. The idea is that you could instantiate a model and then run it over, call the test driver over several structures and accumulate results that way. So let's read the documentation for this. And here, what we're going to change is so the defaults are usually what we want to run on the website. On the website, we kind of want to go as far as possible. Here, I run the compression until until it collapses to 1/4 1/4 of its original volume, and I run the extension or negative pressure or vacuum until it either vaporizes or gets 4 times the original volume. That would take a long time to run. So we're going to change these arguments, minimum fractional volume to maximum fractional volume, to something much smaller, just ±2%. And we're going to run this on HCP silver, which isn't the ground state of silver, but I wanted something anisotropic. So I'm going to and compatible with that EMT calculator. That's a Jupyter bug that keeps popping up. Has nothing to do with OpenKim. It's not my fault. So it's gonna run and is gonna do a relaxation at every single pressure step. I'm actually not sure why this is being so slow considering this is running locally. But yeah, so this is gonna run over all the scans and then run over all the pressure steps. And again, at every single pressure step, it's recomputing the crystal structure. Eventually, we might add options to be able to skip these kinds of things, but these protocols are really meant for the OpenKim website first and foremost. But we've always had requests from users saying, "Hey, how can I run this locally?" And our answer is always, "Well, you got to install the Docker and figure it out." So we're trying to make that easier. So it's completed the compression scan because it exceeded the prescribed volume range, and now it's doing the scan under vacuum. There we go, it's done. It's going to show all these plots. It's going to show it is anisotropic. It's not changing a lot because it's a very narrow pressure range, but you can see that the C/A ratio actually is changing as you compress the crystal or put vacuum on it. And then just finally, the final small feature of KimVV that I wanted to show is that in addition to getting the results as a Python dictionary, you can also save them to a file. We save our data in the so-called Eden format. It's very similar to JSON. There's packages for reading it and writing it. It's not, no reason to go super in depth with it, but if you specify this file, it'll also save all the auxiliary files generated by the computation to that path as well. So if we run this, and then browse, we can go to scan output, and we can see that here it reports the coordinate file at every single pressure step, and then all those plots are here as well. And the results.eden file, I guess I can show you what the Eden file looks like. Very similar to JSON, just a dictionary containing all the
all the results. And if you want to plot it yourself, you can use that. So that is that I believe is everything I had. Gonna again flash this last slide that I showed that I had in my 15-minute presentation, where you can get more info about OpenKim. You can go to the website and read our documentation. You can email us directly at support@openkim.org. The best way to get help is probably on the matsci.org forums, which is a discussion forum coordinated by OpenKim and Materials Project, and that has nearly 40 participating projects, and that's where the LAMP support forum is as well. And I want to also advertise Kim Initiative, which is the kind of broader initiative, including OpenKim and several related projects, such as CollabFit, which is a project for that archives and provides fitting data, first principle fitting data for interatomic potentials, with the same kind of rigor and provenance as Kim does with interatomic potentials. And we also have Fermat, which is a ML project that is aiming to provide to create a foundation model and for material science and a material generation, generative AI for materials. So thank you very much. This concludes this breakout session. And if anyone has any questions, please let me know. I'll look in the Slack as well.
Now we have a 15-minute. Sorry, we now have a 15-minute break and then come back in here. We'll have the very last session of the workshop.
Oh. All right, we're going to start now with the last session of today and this workshop, the developer session, starting with Stan Moore. But before we do that, no developer session could be done. Hold on. Stop sharing. Could be done without Axel. So, hey, Axel, are you here?
Here I am.
So now we're complete.
Okie dokie.
Looking
So
good.
I'm virtually in Albuquerque. Aiden probably will recognize the picture.
Hey, Axel, did you apply a zoom filter to your beard?
No, I actually applied a knife and I don't need it anymore. I'm not teaching anymore. So
Okay, so Stan, take the stage.
All right, just let me share my screen.
It's probably mine.
Perfect. Yeah, that looks great.
Zoom out a little bit.
Okay, I'm Stan Moore. I'm one of the core LAMMPS developers at Sandia National Labs. So I'm going to talk about two topics. The first is COCOS and COCOS and LAMMPS, and then the second is LAMMPS development and some recent work that has been done by developers, mostly Axel. Okay, so I don't know that GPUs need a lot of introduction, but according to the top 10 list of supercomputers, 9 out of the top 10 use GPUs. I've watched that, grow over time in the last 10 years from maybe 1, and now it's 9. All of the exascale machines have GPUs, both AMD and Intel. And then there's also large supercomputers from NVIDIA as well. And to run on these GPUs, you really need special code. So LAMMPS, vanilla LAMMPS is just regular C++ and MPI, but that really doesn't cut it for GPUs. You need something more like CUDA or HIP, SYCL, or OpenMP Target. Okay, so there's several different options in LAMMPS. We call these accelerator packages beyond just the vanilla C++ code. So there's the OpenMP package, written mostly by Axel Kohlmeier. It's native OpenMP threading, so that's a CPU-only accelerator package. There's also the Intel package. It's like the OpenMP package, but it has enhanced SIMD vectorization, so it's a lot faster if you can vectorize your code. But it's also very complex if you look underneath the hood. And there's a GPU package, which Trung talked about yesterday. So that's native CUDA as well as OpenCL support. But the main difference of the GPU package between the Cocos package is that the GPU package only runs the force calculation and a few other kernels on the GPU, and then everything else is running on the CPU, like the fixed NVE, time integrator, any computes, etc. The Cocos package uses the Cocos library, and then it, like Anders said, it tries to be GPU resident, meaning everything runs on the GPU, and it supports all three major vendor GPUs from NVIDIA, AMD, and Intel. Okay, so Cocos is an abstraction layer between the programmer and all of these different platforms. It allows the same C++ code to run on multiple hardware, both GPUs and CPUs. And so the idea is that we write LAMMPS once in Cocos using these abstractions, and then when a new GPU or a new supercomputer comes along, we change Cocos or we add a new backend to Cocos, and we don't have to change LAMMPS. Cocos consists of two main parts. The first is mapping kernels onto these backend languages like CUDA. And then the second part are Cocos views, which are, you can think of them as kind of like polymorphic memory layouts or smart arrays that you can change at compile time to optimize the layout for a GPU or a CPU. Cocos is used on top of domain decomposition in LAMMPS, so it's MPI plus Cocos, and it's open source on GitHub, and it's used in many, many projects, not just LAMMPS. So we've taken the Cocos library and we've implemented into LAMMPS, and we call that the LAMMPS Cocos package. I mentioned it tries to be GPU resident, but that also means that if you have something like a fix or compute that's not yet supported by Cocos, you have to do data transfer between GPU and CPU, and that could have an overhead. It's only double precision, but single and mixed precision is in progress. There's a few different options that are controlled on the command line by the package Cocos command. You can see more in the LAMMPS docs. And so in order to run a script with the Cocos package enabled, you just have to add a few things. The first is to turn on Cocos. So that's like this -k on G4. And then you also need to add the suffix command -sfkk. Similarly, if you want to run on a CPU with OpenMP threading, then you turn on Cocos and then you set the number of threads, and the suffix command is the same. And so what this does is it will try to, for any style in your input, it will try to find a Cocos version and use it. Otherwise, it will fall back to the vanilla non-Cocos version. Okay, so since this is the developer session, I want to just touch really briefly on the actual code. We're going to look at porting a simple pairwise potential. So this would be like the Leonard-Jones cut, LJ cut. And for any simple pairwise potential, we actually have an abstraction called pair Cocos. And this really handles all of the messy details of Cocos, of how to launch kernels on the GPU, how to do this threading over atoms and sometimes neighbors. And the only thing you need to do is implement two kernels, just the pairwise energy and the pairwise force. You can copy and paste from the closest existing style. So for example, LJ cut, KK, just copy and paste and treat a lot of it like boilerplate or boilerplate. plate code. Okay, so this is just the standard Lennard-Jones per LJ cut.cpp. This is the compute function here. And we're doing a loop over atoms. So this is a loop over the neighbor list. So this is like the central atom, and then here is the loop over the neighbors. And then you compute the Lennard-Jones force and also the Lennard-Jones energy. So it's a pretty simple potential. You know, it's just the R to the 6 and R to the 12 potential with some coefficients. And so this is really all you need to know in order to use this Paracocos abstraction. So now I'm going to show the Cocos version. So this is per LJ cut Cocos. And again, you can just, a lot of this just treat it as boilerplate, just copy and paste. And then the only thing you need to change for your potential, if you're implementing a new pairwise potential, are these two kernels. So here is the force kernel. And so this is the force between two atoms. And you can see that it's really similar to just the vanilla non-Cocos version because we've abstracted away basically all of the Cocos. So if we go back here again, this is the force. So you have some pair coefficients, and then this is just the R to the 6th term and R to the 12. Similar for the energy, you have more coefficients. And so I'm going to just go back one more time. And so here's the energy again. It's very similar. F float, you can just think of that as double. It's just an overridden type. But this is literally all you need to do for a simple pairwise potential. And so if you have any questions, feel free to reach out on MatSci or there's also a detailed Cocos tutorial that goes into depth of, what if it's not a simple pairwise potential, that's on YouTube. There's documentation on the Cocos package. You can ask questions on MatSci or GitHub or, email me. My contact is on the LAMMPS website in the authors or developers tab. You can also look in the LAMMPS reference paper. It's more of a general overview of LAMMPS. So like I said, if it doesn't fit into this Paracocos abstraction, then just copy from the closest existing Cocos file, and I'm happy to give consultation, advice, or even help out. Okay, so that was topic number 1. Topic number 2 is LAMMPS refactoring and testing. So these slides were adapted from Axel, who I'm really happy he can join. So apologies in advance, Axel. I'm going to go through just a brief history and just talk about a few of the recent work that we've done in LAMMPS. So LAMMPS, as you probably know, started as a Fortran 77 program. Then it was rewritten in C++. And we're trying to modernize LAMMPS by like in 2020 required C++ 11. And we're soon will require C++ 17. So for the LAMMPS development process, it's a really continuous release. We want LAMMPS always to be useful, so we're constantly pushing to GitHub. The main development branch on GitHub is called develop. And then we also have a release branch, a stable branch, and a maintenance branch. So, if you submit a pull request, it gets reviewed, it gets merged, that goes into develop. Every few months, say every 2 to 3 months, we will take all the changes in develop and then we'll create a release. And then about once a year, we'll update our stable branch. And then If there's bug fixes after release is stable, those are backported into the maintenance branch. So you can see here this flow chart. So if you have a pull request, it goes into develop, and then into the release branch. After a feature release, we'll tag a patch with a date. And then about once a year, we'll do a stable release, and then we'll backport bugs into maintenance. So you have some code, you want to get it into LAMMPS. How does that work? Well, this is one workflow. It's not the only way you could do it, but this is what we suggest. Create a GitHub account, upload a SSH key so you can push to GitHub, and then go to the LAMMPS GitHub site and create a fork of LAMMPS. And then once you've created your fork with your user ID, then you're going to clone it on your local machine. You're going to point to the public main LAMMPS Git repo and set that as an upstream, and then pull in the changes, and then connect your develop branch to upstream. Okay, and now say you have some code, you want to create a pull request, or even you just want to work on it. You're going to take the develop branch, which is in sync with upstream LAMMPS, the public main LAMMPS. You're going to check out a new branch that's based on develop. And then you're going to make some changes, and then you're going to push those changes into your new branch. And then when you're ready, you can submit that branch as a pull request on GitHub. We'll do review. You may need to make a few changes. And so you can, or we may also make some changes, and then you'll need to pull those back into your branch. You can see the commands here. You can also have multiple feature branches and just switch between them. But our suggestion is that keep your development branch in sync with upstream. So our guidance is basically never commit changes to your develop branch. And if you need to undo it, then here's a way to undo it. You can also, before you submit a pull request, you can test your code. There's some checks. So the commands are here, like make check, look for white space problems, make sure the documentation builds, etc. These checks will also run automatically if you submit a pull request. You can also run the unit tests with CMake, and so there's some documentation there. There's also a newer GitHub command line interface. I've never actually used this yet, but it's high on my to-do list. It really simplifies the testing and reviewing process. And so instead of having to, this is maybe more for if you're like a core developer or testing like these pull requests, but basically you don't have to add other people as a remote. You can just have these shortcuts. So say there's a pull request 4304, instead of having to go and look and like add a remote for that user and then pull that into your branch, you can just check out that pull request by the number, which is really convenient. Okay, so that's about LAMMPS development, like GitHub and pull requests. The last thing I'm going to talk about is some ongoing projects. So a few of them are improving the error messages to be more specific and helpful, replacing the C-cell strings with C++ strings, specialized classes, making better use of utility functions, and then improved accessor functions like for the fixed compute group and region styles. And this is not a complete list, just a few highlights. Okay, so to be honest, in the past, the LAMMPS messages were pretty terse and maybe not very user-friendly. For example, illegal group command or something like that. It would show the source and line file, but that's less helpful for users, more helpful maybe for developers. And so we've been working on making the error messages to have more information so that it's easier to figure out what the problem is. And then we've also been adding actually URLs that will point to a more detailed explanation in the manual, and I'll show that in a bit. So really, we're just trying to add more information, to be more specific, to tell what's missing, etc. Okay, so we also have this utils error URL. It's pretty well implemented. I just want to do a quick demonstration. So these are many of the errors that you might encounter. So for example, non-numeric atom quartz or pressure simulation as stable. I think that one comes up a lot. And so when you see this error in LAMMPS, it will actually now have a URL to this paragraph in the documentation, and then you can click on that and get more information about that error. And so that keeps the log file output short, but gives you a chance to understand better. So, and there's many errors, so we're trying to improve the output without making the log file huge. Let's see. Okay, we're also, and again, this is a lot of work by Axel and others, working on replacing char star with standard string. This allows us to use a lot of helper functions in the utils class. And one thing that I really like and that's really helpful is you can use a regular expression with these strings and the util string match here. And so if you want it to, you want to match rigid, but all the fixed rigid styles including Cocos, so like rigid / KK, you can use this regular expression now, which is really convenient compared to like the C style string commands. So code simplification. So again, there's these helper functions in the utils command. So the log message will print out both to the screen and the log, and it now accepts variable numbers of arguments, and you can use the FMT lib library, which will help instead of having to like create strings manually and pass them in, you can just put in the arguments with FMT, which is really convenient. So this can lead to a lot of code like simplification. So this is a before example where you have this add compute, and now with the FMT library, it's only 3 lines instead of this huge code block. So it's really convenient. Porting external code. So LAMMPS, we try to keep it modular, but maybe not everything is appropriate for like being included into the LAMMPS distribution. And so one option is to use the LAMMPS plugin feature. So there's this plugin repository, and the bar for acceptance is a lot lower, so that you don't have to include documentation. Even, maybe there's known bugs or it's contributed by somebody else and may not be maintained. You can use it as a plugin to LAMMPS. It's also compatible with Windows as additional packages. And this is one way that we can support external code, but it doesn't have to have the same requirements, the strict documentation and testing and everything that would be required for inclusion inside the mainline repository. Okay, and finally, Axel's been working really hard on tests. He's added unit tests, tests of functions, individual commands, some of the interfaces, Python, just tons of testing. And why do we want testing? Well, we can catch bugs early, and that can save time and money. We can make sure that we didn't break anything. We can, encourage modular programming, and, just make sure that everything is working. And so, even if you check out version of the day LAMMPS, we want that to be stable. We want that to build and not be broken. Okay, so with that, I'll take any questions. Otherwise, we're going to have an open discussion. We can talk about feature requests. We can talk about questions about LAMMPS development or really any topics, and that's the rest of the breakout session.
Any questions for Stan on what he talked about? Questions for Stan on what he talked about? Oh, sorry. Mike's not on.
For the people online on mic, are you using AI to help in your refactoring?
So
How would you?
Yeah, so you mean for the testing or?
No, I mean for actually refactoring the code.
So we do use GitHub Copilot to do code review. I've experimented with like ChatGPT to try to help me Cocoa size code, and it was a while ago and it wasn't very successful, but I need to try that again. I think it's come a long way. Axel, do you want to comment? I don't know. Can he talk or not?
I can talk, yeah.
Okay, good. Yeah, dude.
Stop sharing, you can also see me.
Yeah.
The problem really with AI tools is LAMMPS is very idiosyncratic in how it's been written, and there's a lot of assumptions that are made that an AI model doesn't know about. And that makes it often do bad suggestions. So the GitHub Copilot is good for finding typos, but it regularly makes wrong suggestions.
Yeah, so it's close, but not quite. Yeah. So yeah, like when I try to have it port Cocos, I think now our internal tool will allow us to upload files, and so I could kind of teach the AI and say, this is a good example, and this is what I want you to do, and now here's some new code. Can you do it? But just with the out-of-the-box ChatGPT, it didn't work well.
Yeah. Yeah, and even with other code assistants like Claude, at least with things that I've tested on, the models I've tested maybe 4 months ago were not good enough for writing actual MPI codes. So what they produce is a whole lot of C++ code that might seem reasonable based on your specification. But when you then look at what it actually produces at a technical level, it is not aware of how an MPI program operates. So it produces MPI code that is fundamentally wrong because it doesn't understand how that functions. So that's my experience.
Yeah, well, that's one thing, but the other thing is really the physics. So a lot of LAMMPS knows that certain things can't happen because of the physics of the problem. But then if you put a generic tool on it, it makes all kinds of useless suggestions for situations that don't happen. So right now it's taking more effort than it's helping. One more thing I would like to add to this is we make extensive use of static code analysis tools. So again, in the hope of finding bugs before actually a user tells us that he gets funny results.
Yeah, but those again have a lot of false positives, so we have to screen out too. So
Yeah, but that's heuristic. That's not really artificial intelligence.
yeah. Other questions before our open discussion?
Well, I was just going to predict 10 years from now, we have the LAMPS workshop. Maybe no developers will be left or need to come, and the code will just be evolving with Chat GPT prompts. So, all right. Thank you for that question. It was a good question. Any other questions on the topic Stan brought up in his remarks or for Axel?
Hello. So this is a question more about what we saw in the first day. Can you comment on what the next steps are going to be for the LAMMPS GUI project?
Yeah, that's a good question for Axel.
Right now, well, if I have the time, I should actually do a rewrite because it was put together very quickly. It's very inconsistent and getting hard to debug. For new features, that's more a question of feature requests from users. What I'm currently working on is trying to improve the visualization. So like for example, for many body potentials, you don't see bonds, but I want to make dump image be able to automatically draw bonds. And I also have written a feature for VMD to visualize regions, and I'm currently in the process of porting this to dump image. So you could basically, in the image viewer, get a list of available regions, and you can turn them on and off so you see where they actually are. I found debugging regions very, very difficult. So I was always using create atoms to put something there where the region is to see whether it's actually in the right place.
Yeah, did you have a specific feature request?
No, it's I didn't know that the GUI existed, so I'm trying to see where it's going, but I think it's a good answer.
So Axel, if someone does have a, observed bug report or a feature request for LAMPS GUI, do you prefer that on the LAMPS GitHub page or the LAMPS GUI GitHub page?
There is
Or
no
either.
LAMPS GUI GitHub, at least not yet.
So I didn't catch what you said.
There is no specific GitHub for LAMPS GUI. It's in LAMPS itself.
Oh, okay. So putting those just in the regular LAMPS feature and LAMPS bug requests would be fine.
Or in the MatSci forum. So there's often a post where I make an announcement that I have new test versions with some additional features or bugs fixed. So adding a comment to that thread is also a proper place.
Yeah. So I know on Tuesday when we used it in the LAMPS workshop, there were a few small issues and also ideas people had. So I don't know if we captured those. I might have made a couple notes that I'll do, but if you had one of those, you can post it to the.
Yeah. So the two bugs
Axel's already fixed a couple. Okay.
Yeah, the two bugs that I heard about, well, actually 3 bugs. The third was already fixed, but the other 2 are now also fixed.
Nice.
Okay.
Thank you.
I'm remembering now, somebody was probably Ilya asked if OpenKim is included in the LAMPS GUI build. Okay. So there's a feature request.
That's kind of tricky because then I need to bundle it a bit differently. So it's more a packaging question than a technical question.
Okay. Well, Axel, you and Ilya could iterate on that a bit. It was something he was interested in, so.
What we can always do, I'm not doing this right now, but what can be done is you can compile LAMMPS GUI so that actually LAMMPS itself is not linked. You can then in the preferences give a path to a shared library, liblamps.so, and the GUI will load that shared library. So basically, you can build your own LAMMPS version, and then without having to compile LAMMPS GUI, you can load LAMMPS into that package.
Yeah, that's actually a good workaround, but go ahead.
Yeah, sorry to butt in, but that might have to be done regardless because you'd either have to bundle it with the Kim library, and then you can't do it on Windows, for example, or you would just have to compile it with some Kim library and assume that it's findable and it'll link dynamically. So there's definitely some implementation questions to discuss there.
Yeah. I mean, in that case, I should probably make it a habit to provide both kinds of packages. Right now, it's mostly for convenience. I mean, it's meant for tutorials, and we don't have yet any tutorials in the tutorial package that uses OpenKim. So basically, if you convince Simon to put in an OpenKim tutorial into his website, then we would have to figure out a way to have LAMMPS GUI updated.
I'll definitely put that on my to-do list.
Yep.
All right, another in-person question.
So this is kind of half of a request and half a question on if this is already happening. But an update for LAMMPS GUI so that it is compatible with HPC computing and sending requests to clusters.
That will not happen. You cannot easily run the GUI and with MPI. That creates a mess.
Yeah.
But the point is, I mean, there's nothing special about LAMMPS GUI. The input file is just a regular LAMMPS input. So just scale, develop the system on a small scale, and then just scale it up and run it on the cluster.
Yeah, so you can copy paste the input that you get and then run that on a cluster. You can also use OpenMP threading to use, up to say 36 or whatever, however many CPU cores you have on a node with shared memory.
Yeah.
But it just is not feasible to use MPI to go more than one node.
But you can see why somebody might like that as a request. So
Yeah.
Okay, thank you.
So Axel, there was another question a couple of days ago about LAMMPS GUI. Does it run using GPUs with Cocos?
Not Cocos. We're missing the introspection. So with Cocos, I get a crash if I compile it for a GPU and don't use the GPU. With the GPU package, that's not a problem. We're supporting Cocos OpenMP right now, but the other, it's a tricky thing. And also, I need to find out whether there's a viable GPU in there. And Cocos will just tell me, oh, I can't do this, and the GUI will crash. So right now, that's a bit of a problem. That's also why we can't do the unit testing safely on Cocos with GPU, only Cocos with OpenMP.
It's probably even more tricky on Windows and Mac, I guess, because Mac doesn't even have that.
Yeah. I mean, the precompiled versions, the GPU package uses OpenCL, so you have to have basically the entire GPU support available. One thing we discovered just this week is that also Flatpak, even the binary is capable of using OpenCL. There's no OpenCL in the Flatpak sandbox, and so the GPU acceleration is not flagged as available in the preferences.
So I was just thinking a bit about the previous question about running with MPI or running on a cluster. I mean, there are batch managers or workflow managers that have APIs, right? That they talk to the cluster or to the supercomputer facility and do things. It seems like it would be possible that LAMMPS GUI would have a button or an option or say, ship my big version of this calculation off to that API, and the workflow manager would know how to do the rest.
you can do this. I've seen this, for example, with the Schrödinger software, and it's so messy. I don't want to do the programming.
Okay. I tried.
So, but it does sound that if somebody wants to program it, you might be able to make a pull request for it. If it gets merged is another question.
Yeah, somebody has to maintain it. I mean, technically, it's possible to even have a graphical application use MPI. I think ParaView, for example, can do this, but it just is such a mess. And LAMMPS GUI, I just shied away from anything too complex. The whole library interface thing and querying the running simulation, that's messy enough as it is.
Yep. Okay, so let's broaden the discussion a bit. If you still want to ask about LAMMPS GUI, that's great. But the second or last part of this session was meant to be a brainstorm with anybody who has ideas, either simply from a user perspective or from, a development, new feature perspective of things you would like to see in LAMMPS or attributes of LAMMPS to make it easier to use, or add your favorite model that's not in the code, or you want to know if it can do something or how it could do something. This is a good chance to, throw out your idea and let us hear about it.
So I have a general question for all the users, developers. Just because I'm a packager and also Christoph has been packaging LAMMPS for several years for Fedora. Generally, I'd like to know how are people getting LAMMPS and what are they using to build? So first of show of hands, who's using the makefile based build system of LAMMPS? The traditional make. Yeah. Okay. And how about the CMake based build system? Okay. Yeah. Okay, so the majority of you are building from source yourself. Is anybody using something else, like getting a packaged version of LAMMPS from somewhere? Conda, SPAC, Fedora. Okay, that's minority. Okay. I think that's, Christoph, do you have any other? That's pretty much, yeah.
Question.
Okay.
Yeah, comment. It might be a minority in this room. I don't know if this is representative. I'm definitely biased towards Conda for ease of distribution, but I'm surprised that Conda is a minority.
No, I myself am the maintainer of the SPAC package, so that's I think a majority from supercomputing centers, but hard to say if this group.
Actually, I mean, when you're inside of a company, using Conda typically is a very difficult thing to do. So that's why I personally always just pull the source and compile. The unfortunate part is like if you use CMake, you don't have a lot of control, and it's rather opaque to me how to change that. So that's why I use both. But I know that our cluster managers like CMake because they compile them too. But using Conda is a problem because, you have to deal with firewalls and they don't like stuff from outside that is precompiled, et cetera, et cetera. So.
Can you do me a favor? Can you send me an email with the changes that you cannot find in CMake? Because everything should be accessible from CMake. It's just a matter of documenting or finding the options.
Actually, the simplest thing is I have my own internal packages. And I have to basically start editing the CMake text files to add that package to it, which makes it a little difficult. So that I don't know how to do that in CMake. We can talk about that offline, but that for me is like the one of the reasons.
Yeah, well, this is one of the problems that is a result of having to support both the traditional build and the CMake build. If we would be only CMake, it would be extremely straightforward for people to add packages automatically.
Yeah, so I just want to make a comment too. Hope you're aware, but we're planning to deprecate the makefile build for many packages, including Cocos and the ACE. So if that gives you heartburn, please let us know soon.
Yeah. So
I'll make one explanation of that statement. So this would be, I mean, LAMMPS has like 100 packages. The kind of packages he's talking about are ones that have external dependencies or auxiliary things they need to load. So if it's things that are just kind of pure source code, then that's not a problem for traditional make. It's supporting traditional make for all these special cases that are becoming more and more complex, especially with machine learned potentials and PyTorch and other kinds of auxiliary software that are needed to run them.
yeah, I mean, I'm kind of along that same line. There's a lot of those machine learning packages that are not in LAMMPS itself, and you have to download from somebody else's repository, and then you build it. And I cannot do that with CMake. I have to do Make. I don't know how to do it with CMake. And one of the other fun things with all of this is that I occasionally hit it where some of those extra packages are not compatible with other extra packages. So I have to have multiple versions of LAMMPS, or they're tied to certain specific LAMMPS. And so that's another issue that I have, that I have to have multiple LAMMPS executables of different versions and different install packages across all the different potentials. So.
Okay, so Richard's probably best on that, so I'll let you comment on that.
No, I mean, it would be good to know which are the incompatible things that you run into. So just so we can document them. I mean, there's in the documentation page, we have a list, but for any particular things you run into, let us know.
Now I have to think about what I was going to say.
Can you speak up, Peter? Because I could barely hear you the first time.
I'm mumbling to myself. What was I going to say? It's my jet lag. I'll think of it. Okay.
Other comments on this topic of building and you know, how you get LAMMPS and how you build it, or especially if you're developing new things, like Lucas talked about, how you find it easy or hard to maintain your own local versions with things added?
My old age is actually catching up with me, but now I thought of what apparently was important, so it came to me again.
Louder.
Actually, my issue actually is that since I maintain my internal stuff, which depends, of course, on core LAMMPS, it changes so much, even in like, a year or whatnot. I typically only download maybe a version every other year or so, because it takes me a long time to get everything to match again. Now, my bigger question there is there such a need for touching core LAMMPS as much as you guys do? Now, let me put the caveat in. I appreciate the effort. Don't get me wrong. It is just a question.
Maybe can you specify what, like an example of what changed in core LAMMPS that broke your EMC?
It can be something with neighbor lists. It can be something with what are they called? Ensembles, so NPT or stuff like that. It's kind of like all over the place, that it typically needs alterations. And of course it converges in the years, because I've been doing this already for the last 20 years or so, and stuff is converging as it is. And it's not as like problematic anymore as it was. But I see that, for instance, STL libraries are introduced and then sometimes they disappear again and whatnot. So I can't really put my finger on it to say, like, this is this specifically, but I see that the core is changing. And for me, it's kind of like, well, it's supposed to be core. Is that not supposed to be stable? So that's kind of like the philosophy behind my question. Now, again, don't get me wrong. I appreciate that you guys are working as much as you do on it, because the whole community really is benefiting of it. So this is more maybe like a little thing that I have.
Yeah. So the problem is that we still see a lot of things where LAMMPS is showing that it was originally written in Fortran, and it's just against best practices that you mess with internal data, and you have to know exactly what you're doing. So for example, the neighbor list requests. If it wasn't a pair style, you had to like set the pair flag to 0 and then the fixed flag to 1, and you had to know this. Now it's set up in such a way that you pass a this pointer and there's overload. So you just do a request and it automatically does a consistent set of flags and you don't have to update something. For example, you have packages that were developed a long time ago that don't know about new features and additional flags that exist. So if you do this all inside the code and use abstraction, hide as much of that from the individual usage, then we're actually long-term more reliable. The question really is, what's a stable API and what's a desirable API? I also should point out that there is a page in the documentation where I tried to update every change that may require changes to other source code to be up to date. So that page is something where you could look for changes that you need to do and how to do it.
So one question would be, would it make sense to have a more formal deprecation schedule? So when we use Cocos, they have, you know, guaranteed backwards compatibility between major releases, and they'll deprecate, but then they won't remove it yet, and they have a way to, you know, turn on the deprecated code so you can still use that.
Well, in order for us to do that, we had to have a stable, we have to define an interface that is, we have to make that distinction, what's part of the interface and what's not.
Yeah.
And so anything that touches that interface, we could make guarantees on that. But right now we don't have that formal definition of what the LAMMPS API is.
Yeah.
And that's part of the problem of our installs. Do we install all the headers that are part of our compilation, or do we have a minimal set, like the library API? The library API is something where we already specified, okay, that's pretty much stable. If that doesn't change, sure. But the internals within LAMMPS, we haven't so far specified what the guarantees are on that.
Yeah, so something to think about.
Yeah. Good point, Peter. Other topics or ideas? You know, Marcus Martin here has written many Monte Carlo codes. He would love to hear about Monte Carlo features you would like to have in LAMMPS. For example, he and I were talking about this earlier today.
So I will say that we're actually working on a Gibbs ensemble implementation in LAMMPS. It's not ready, but we have a postdoc that's working on it.
See, I didn't even know that, so I didn't mention that to you.
We should talk.
Were you saying something else, Marcus, before?
No, that's the place to start. I mean, after that would be, I have a natural bias towards configurational bias for molecules, so that would be my thing afterwards.
Yeah, Peter has a comment.
I'm actually not too familiar what LAMMPS can do currently with bond making and bond breaking and all that kind of stuff, but Monte Carlo kind of like thrives on that. And so if you have bond lists and angle lists and whatnot, those are unnatural when it comes to Monte Carlo. And when you do MD, those are very natural. So sometimes, you know, you can do it differently. Like I do it myself by creating these things on the fly. But that's not how LAMMPS is constructed. So to build in Monte Carlo into LAMMPS is not trying to put a square peg in a round hole. I don't know. It's just maybe a rhetorical question. I don't know.
Yeah, well, I will say we do have some MC capabilities, like the grand canonical Monte Carlo, already in LAMMPS.
Well, the big challenge is that Monte Carlo steps usually don't parallelize easily.
Oh, sorry.
Oh, well, related, yeah.
So Monte Carlo and LAMMPS has a long history. It predates my arrival at Sandia, and I'm still scarred from my early attempts to make sense of what my predecessors had done. But there is a reasonable amount of Monte Carlo support in LAMMPS right now. Axel will probably agree that it is hard. It is some of the least maintainable code in LAMMPS, and that has a lot to do with the nature of Monte Carlo that does not play well with LAMMPS data structures. But it's also to do with the fact that these Monte Carlo capabilities were added incrementally over time without a clear grand plan. And we saw a nice talk yesterday from Laura Zicki showing how a different approach to calculating energy differences could actually give us the scalability and generality for Monte Carlo that we have come to expect for all other aspects of LAMMPS. And so there is hope that we can sort of make things better with the existing code. However, I think there is an opportunity to start from scratch and write a lot of Monte Carlo functionality in LAMMPS in a completely different way that is not constrained by poor decisions that people have made in the past. And so if anybody's looking for an exciting new opportunity to get glory, I would encourage them to go after this. It would not be hard to replace the existing functionality. I guess that's what I'm saying.
So kind of following up on what Aiden talking about Laura's talk yesterday, are you planning on doing sort of this like where you can use domain decomposition for the new Gibbs ensemble method so that you can parallelize like insertion or like swap moves? That way you can test it in more spots sort of simultaneously.
So right now we just followed the grand canonical Monte Carlo paradigm, but we have two boxes. Typically with Gibbs ensemble, you don't need a huge system, right? Because you're just trying to get equilibrium bulk properties, liquid and vapor. But yeah.
So when it comes to like grand canonical ensembles, are you guys actually doing insertions and stuff like that? As in like growing molecules in there? Because there you would need something like concerted rotation and configurational bias and all that kind of stuff to actually do that.
Yes, we do insert molecules, but we do not grow them. So there was around about the time that Marcus, Martin, and I were both getting started at Sandia, there was a fork of LAMMPS called Ladera that actually did configurational bias Monte Carlo in hybrid MD-MC. And it was an absolute nightmare. And I don't think anybody should ever try to do that again in LAMMPS. But I would be happy to be proven wrong if somebody could come up with an elegant way to sort of encapsulate all the complexity of configuration bias and separate it from the complexity of LAMMPS. Maybe it could be done. I don't know, but it would require some cleverness, that's for sure.
What comes to my mind is that you could actually grow things using fix adapt.
So fix adapt is a general tool to let you scale a parameter over time
so that,
as LAMMPS run.
You could apply that to like continuous fractional Monte Carlo rather than configurational bias, which might play a lot nicer with an MD engine potentially. I don't know what Marcus thinks.
Okay.
I mean, configurational bias is in essence nothing more than a sampling scheme. You can actually also parallelize that to a certain degree. I also in a gray past did do like bond making and bond breaking, and you can actually do kind of like, bypasses of the neighbor lists. So do you create an extra one? So because if you break a bond, you get more neighbors and you need to stick it in there somehow, and you can do that with bypasses. So there's ways to kind of like make it work with LAMMPS, but you get a little bit to the point of like putting a square peg in a round hole because the code hasn't been developed to do that. And so it would actually kind of like need it ground up. You could create, I would assume, like, a side idea of doing that. But then you would also be well advised to a priori design a good way of doing that so that it is a platform that you can build on for later, and not what Aiden was saying is like, we tried something and some people did this and other people did that and nothing really mixes and matches and it becomes a nightmare to maintain. So design at this point in time would be a very important thing to do. So if there is a big need for doing this, then I think thinking before you act might be a smart thing to do.
So was somebody gonna have a follow-up? Okay.
Well, as somebody who wrote a giant Monte Carlo code, why would I think of putting a square peg in a round hole? It's because there's a whole bunch of stuff in LAMMPS that is a pain in the butt to put into my Monte Carlo code. Like, I don't want to think about a GPU ever. I don't want to implement even more potentials. I've already implemented 100 force fields. I'm kind of over that. I'd be quite happy to use something else. And there's a giant room full of people and a world full of people already using LAMMPS. So if you could take the tools to LAMMPS, and even if it meant it's not a super parallel version of LAMMPS doing Monte Carlo, it still might allow a whole bunch of people who are already comfortable in a package to do something that's different. So that would be the concept. Is it easy? Definitely not. But I'm at the point where I need to rewrite every data structure in Tohi if I want to implement the things I want that are new, like continuous fraction, like some of the various configurational bias methods of McGinn. So instead of, if I have to start over anyway, why not start over in something where there's something I'm getting besides just what I write? So if people are interested, let me know.
Yeah, what I want to suggest is the people in this room who just self-selected into a Monte Carlo discussion, continue those and other people can join. I don't know if you want to do it on like a LAMMPS issue page or a LAMMPS feature page or something where you're brainstorming that, so at least the ideas are recorded. But maybe you want to do it just totally offline and come back to us with ideas or a plan, and then the developers can maybe weigh in a little bit too. Okay, so I think technically we're near the end of our hour, but this was kind of open-ended and we're ending early for dinner anyway. So that's still fine if somebody wants to bring up a discussion or an idea, and it could be as simple as it's hard to use LAMMPS because I can't find this or I can't figure this out, or just something. I mean, they talked a little about, I think it was Axel and Stan, about how we've tried to make error messages a little more self-explanatory, or give you a URL where you can find a bigger description than we want to embed in the code. So that was, a clever idea, and they implemented it, and hopefully it's useful to people. But if something as conceptually simple as that would be helpful to you, you can bring it up. It doesn't have to be a sophisticated, how do I write this in C++ or Python question. Can't hear you. Yeah, I hear you. Okay, well, maybe we've run out of energy, which is fine too. Let's thank Stan and Axel for all the contributions to this session. I don't see where Aiden went. Is there final announcements? Okay. Any final announcements we need to make about the workshop itself?
You want to talk about dinner?
Yeah, we'll do that second unless there's other workshop business. Okay. Okay, well, let's mention dinner. I think I already know what Aiden has planned for this. We're going to El Pinto, which is a reasonable drive from here. It's not close. You'll need a ride. But what time is it right now?
4:20.
Yeah, it's probably a little early, but if people want to hang out here a little or go back to their nearby hotels or something, we could meet here at a certain time to make sure everybody's got a ride who needs it. Should we, you said it's 4:30 now?
20, yeah.
4:20. Oh, go ahead. Yeah, I don't know if you avoid traffic, it probably might not be half hour, but rather than set a time, well, do some people just want to show up at El Pinto? Otherwise, we could meet here at 5-ish, Aiden, and carpool over. What do you think?
Yeah, I think we could meet here at 5. I'll be here at 5. I'm just going to stay here.
Yeah.
And we could carpool over from here.
Okay.
It's about a 20-minute drive.
Okay. So take it away. Anything you want to say at the end?
No, I guess I want to say I don't feel like the organizer of the workshop because so many different people helped out in so many different aspects. I could go through the list, but I would probably make some mistakes. So you all know who you are, and I think everybody else can see that this was very much a collective effort, which is really great because more and more we're trying to make LAMMPS not dependent on any one person and much more of a community project. And so these workshops, I think, are a good way to sort of make progress towards that. I did want to, even though they're not here, I did want to thank Lisa Ventrello, Phyllis Rutka, and America Gonzalez for all of the work that they did, particularly like applying a weed whacker to the Sandia bureaucracy. Otherwise, I don't think we would have actually been able to assemble in this building. So I'm very grateful to them. If any of you Sandia people see them, please give them a thank you. And I think that'll help us be able to do this again in 2 years. I think anything else? I think this is the first time we did this since 2019, and I was a little apprehensive that nobody would show up at all because of the fact that we've been doing it virtually for so long. I think we've had a pretty healthy turnout. I think perhaps we could still figure out ways to make this more appealing to people. One idea would be to consider a different location next time. It doesn't have to be in Albuquerque every time, and so we could try to change things up by doing this elsewhere. But that's stuff for a different day. I guess I'll just suggest that we all give ourselves a big round of applause.
Okay, bye, Axel.